This course is designed to support learning automation skills and tools for the purpose of testing apps. But before we get into automation itself, we need to talk first about testing. What is testing anyway? I think we would all have a fairly good intuitive idea of what testing is. It's making sure something works, right? Indeed. But as a former linguist, I think it'd be great to dive a bit into the etymology of testing, the background and history of the word testing itself, to get a sense of the roots of the concept. The English word test originally came from a Latin word testum, which referred to a kind of container or pot made of earth. These were pots that were designed to hold very hot metal, and people wanted to heat metal up for a number of reasons, but one was to determine whether there were any impurities in the metal. So, by association, the pot itself became tied up with the act of checking the quality of the metal. And so now we can say that to put something to the test, in other words, to heat it up in the earthen pot called a testum, is to determine the quality of whatever that thing is. You might also have heard someone talk about a crucible, or maybe heard the expression going through the crucible. This word crucible is another word that has a very similar history. A crucible is another kind of container for heated metal. To take our analogy a bit deeper, we can say that testing is therefore the process of applying some kind of energy in some kind of container to determine the quality of something we want to test, something whose quality we care about. Now, what we care about is software. Our job as testers is to get some kind of indication of the quality of the software that sits in front of us. Maybe we developed it ourselves, or maybe someone else did. How do we even start thinking about the process of testing software? There are a huge number of methods and tools that we can use in the process. But one simple way of thinking about it is realizing that our responsibility is to design and bring about the specific conditions, like heating a pot, that will reveal the quality of the software. One common way of bringing about these conditions is to use the software in its normal modes as a normal user. The software is meant to run in certain conditions, and we can simply run it in those conditions, as any normal user of the software would, to determine whether it works the way it's supposed to in those conditions. We could also try to imagine conditions for the software that its developers might not have thought about. These are often called edge cases. The trouble with software is that there can be a near infinite number of conditions a piece of software can run in, and a near infinite number of situations or states it can get itself into, based on user input or other factors. When developers write software, they usually assume a fairly simple and minimal set of conditions. It is the job of a tester to design crucibles, or test scenarios, that show how the software behaves in all kinds of situations. Obviously, if there are an infinite number of situations that software can get run in, it doesn't make sense to try and test every possible case. So, testing becomes a real mix of engineering and creative out-of-the-box thinking, just to figure out what to test. And that's only the beginning. Testers don't have an infinite amount of time to evaluate each potential release of software. Sometimes software gets released multiple times a day. Choices have to be made about what's most important to test, and which additional tools and strategies we need to adopt to make sure that we can test as much as possible. So imagine if you were an ancient Roman tester and people brought their metal to you to heat up and determine its quality. Once the metal starts piling up faster than you can gather logs and heat up your pots, you've got a problem. And you need to figure out not just new and clever methods for determining the quality of the metal, but also the mechanics of how to scale your metal testing practice. Maybe you buy more pots or invest in technology that starts fires faster. Maybe you get super advanced and figure out that by mixing certain reagents in with the metal, you can get an instant read on one aspect of the quality of that metal. Anyway, I don't want to push this analogy too far, but this is very much the situation encountered by software testers. Almost all testing of software nowadays is done in a context that requires great breadth, depth, speed, and scale. It's an impossible set of requirements unless testers adopt some of the same modes of thinking that have propelled software development itself to huge levels of scale. And yes, by that I mean automation. I won't talk more about what automation is now because we have a whole separate unit on it in a little bit. The main takeaway for now is this. Testing is a practice which uses creativity and technology to build and execute special crucibles for software, with the goal of determining the quality of the software to as accurate a degree as possible. We often focus specifically on the technology side of the equation, but never forget that there's a whole lot about the practice of testing which will require your creativity. Let's talk some more about testing, and specifically, let's give an overview of the various kinds of testing that relate to software. So, testing is the act of defining, building, and executing processes that determine application quality. And this is a good definition, but it's pretty general. We can get a lot more specific about the various types and subtypes of testing so we know what kinds of options we have when it comes to defining and building these test processes. The way I like to think about types of testing is as a three-dimensional matrix, or space. Each dimension corresponds to one facet or characteristic of every test. Here are the three dimensions that I see in testing. First, I like to talk about test targets. A test target is basically the thing you want to test. We might call it the object under test, to be more general. In software testing, it's usually called the app under test, sometimes written AUT. But target means more than saying what app you're testing. Usually, we're only responsible for testing one app anyway, so the app under test is kind of a given. What I mean by target is what component or layer of the app is being tested. When we develop software, the software usually has a number of distinct components and a number of distinct levels. We can consider the levels independently and even test them independently if we want. One component or level of an application could be an individual code function. Users don't execute individual code functions. That happens behind the scenes, so to speak. But we could test a specific function in isolation. Another layer could be the layer of an application's API. Again, users don't typically try to access an app's backend API directly. That's something that the app itself would do in order to provide the appropriate information to the user. Yet another layer could be the user interface, or UI, of the app. This is the part that a user actually interacts with. And we could test all of these different layers. We could test individual units of code, we could test APIs, we could test integrations between various back-end services, and we could test the UI. That's what I mean by target. The test target is the answer to the question, what aspect of the app itself are we trying to test? Second, I like to talk about test types. Now, here I mean something very specific by the word type. In this sense, I mean, what aspect of the app's quality are you trying to test? Apps can have good or poor quality on a number of different dimensions. One app might be fast, but perform calculations incorrectly. So we would say that it has good performance, but poor functionality. Another app might have good performance and functionality, but be hard for people who are hard of hearing to use. Then we would say that the app has poor accessibility. Performance, functionality, and accessibility are all aspects of the quality of an app. As apps become more and more important in our lives, we keep coming up with more and more aspects of app quality that become important. And if we want to test all of these categories, I would say we want to implement a number of different test types. So that is what I mean by type. Third, I like to talk about test methods. This category is a bit more straightforward. Basically, method just refers to the procedure used to implement the test. How will the test be performed? That's the method. What are some methods? Well, what we call manual testing is one method. Manual testing is simply the act of using an app the way a user would, or exercising an app component in a one-off way. In other words, it's done by hand, by a human being. You can manually test units of code. You can manually test APIs. And of course, the most common instance of manual testing is manual testing of app UIs. But manual testing isn't the only method. We can also write software to test our app under test. In this case, our tests are considered to be using the automated method. So, and this is the structure I use to help give us an understanding of the various types of tests. There are 3 dimensions, meaning that in principle, the test targets are independent from the test types, and they're both independent from test methods. In practice, not every possible combination of those 3 dimensions ends up making sense, but a lot do. So let's look at some examples. The name unit testing refers to the idea that we are testing a specific unit of code. Unit testing can be described using the different test dimensions in this way. The target of a unit test is typically a single function in the codebase. The type is usually understood to be functionality. We're testing the functionality of that unit of code. And usually when writing unit tests, we are making sure that the specific bit of code in question functions appropriately in terms of its inputs and outputs. We could run other types of tests on single code functions. For example, we could test their performance. But usually unit tests are written to test functionality. And the method for a unit test is usually automation. Now let's talk about UI testing. UI testing goes under many different names. Sometimes it's called end-to-end testing. Sometimes it's just called functional testing. And some people even refer to UI tests when they talk about integration tests. I think most of these other names are a bit confusing, so I prefer to use the term UI test. This makes clear what the target of our testing is. It's the UI of an application. As we talked about earlier, an app has many different layers, but users typically only interact with the UI. When you are doing UI testing, you are running tests from the perspective of the user. Now, UI just refers to the target of testing, and it doesn't specify the type or method involved. And typically, if we don't say anything else, UI testing is assumed to be functional in nature. That is, we are testing the UI's functionality. And of course, we can do this using different methods, whether manual or automated. Another type of testing, which is commonly discussed, is integration testing. Sometimes when people say integration testing, they might mean UI testing. So it's good to make sure everyone's working with the same definition. When I say integration testing, what I mean is testing the communication or integration between 2 different services. Let's go back to the 3-dimensional framework we've been using to unpack this a little bit. In terms of a target or targets, integration testing is focused on 2 or a few components of a larger system. In the world of modern software development, the most obvious candidate for these components would be maybe a set of microservices that all communicate with one another in order to power an application. But the components don't necessarily need to be freestanding services. They could also just be two chunks of a much larger monolithic code base, which are responsible for communicating in some way. The test type, when I talk about integration testing, is usually functional. We could do performance integration testing, but it's usually assumed that we're just talking about making sure the integration works at all. Finally, the test method can be manual or automated, just like any other form of testing we've discussed. But this kind of testing is almost always automated. A good example of integration testing would be asserting that two services communicate with one another correctly, even if the entire stack of the application is not in the picture. Maybe you have one service that reads customer orders from a task queue, does some processing on them, and then sends certain orders to a system that's responsible for physical order fulfillment, in other words, shipping, and sends other orders to a system that is responsible for digital order fulfillment. In other words, emailing digital products or something like that. You could imagine setting up a test environment that just runs these few services, has no front end, no actual real database or task queue. Fake orders could be created in a simple in-memory queue, and orders received by upstream services can simply be included in some kind of correctness assertion, but not actually acted on. This would be a classic example of an integration test. There are lots of other kinds of testing out there, but I hope that you remember the three dimensions we can use to define any type of testing: the test target, the test type, and the test method. The target specifies what thing we're trying to ensure quality for. The type specifies what sort of quality we care about: speed, correctness, visual appeal, etc. And the method specifies how we go about the test itself. Do we use automated means or manual means, or some specific subcategory of those? That's it. This course advertises training for automated testing. Since you're already taking the course, I can assume you already buy into the idea that automation is a valuable skill or concept. But let's take a few minutes to examine why this is in some clear and concrete ways. First, let's talk about what automation even is. I know that we all have an idea of this, however vague. Automation is robots or software doing things over and over again so that humans don't have to. Indeed, the word automatic comes from two Greek words that together mean something which can will, drive, or act by itself. This doesn't imply, of course, that anything which is automatic is somehow intelligent, just that given the right setup, instruction, and context, it can perform actions on its own without human intervention, or with minimal human intervention. Humans have been trying to get out of doing things by hand for a very long time. There are some quite old examples of mechanical automation, from a clock powered by the flow of water, to a weaving loom which can put together a piece of cloth on its own, using a set of punch cards as input to say what sort of pattern should be woven. But with the advent of the Industrial Revolution, simple mechanical techniques became a lot more powerful, especially with the addition of steam and electricity, which could be used as a power source. Now, automation was more than just a thing for wild inventors and hobbyists. It became the backbone of social production. It was, of course, still very much intertwined with human work and required an awful lot of intervention. Eventually, all of this innovation paved the way for a totally different type of automation. The electrical computer, built on top of hundreds and hundreds of electrical circuits. Now, mathematical calculations could be performed perfectly, correctly, and almost instantaneously. This jump from the world of trains and horseless carriages to the world of information was really, really important for us. At one particular point in this history of automation, an MIT grad student named Claude Shannon took ideas that had existed for a long time, from philosophers and mathematicians like Leibniz and George Boole, and applied them to electrical circuits. With this insight, the idea of a binary digit or a bit was put to work in concrete ways. And all kinds of logical calculations could all of a sudden be performed at the speed of electricity. This brought the possibility of automation to information, which is the world we now inhabit. Everything we do on computers nowadays is fundamentally built off of these very basic insights, which is why it's really interesting and important to review them. All software is therefore a kind of automation. As long as software has existed, software has needed testing. So it makes a lot of sense that when it comes to testing software, we would turn to the same kind of automation we used when writing that software in the first place. In fact, automated software testing is not a new thing. At first, testing software was more like writing mathematical proofs that the software did the right thing. Later, and nowadays, software is too complex and too open-ended to be proved correct in this mathematical kind of way. But even many of the patterns we find in regular old automated software testing today have their roots as far back as, say, the 1970s. You could say that automated testing went mainstream in the 1980s and 1990s, and some of the tools we cover in this course, like Selenium, were invented in the early years of the 2000s. In taking this course, you are joining quite a long stream of people who have decided that one very useful way of testing software involves writing software. And when you stop and think about it, it's quite incredible that we can use the very same techniques for testing software as for writing it. This is all due to the immensely powerful framework summed up in the idea of the binary digit, which allows us to encode any information we want as a set of tiny electrical charges, and to decide that some of that information is not just data, but actually instructions for operating on other information. It's really quite amazing. So that's all about what automation is. But what is the promise of it for us? Like the many people who have turned to automation before us, automation is always there to solve a specific problem, usually one that we have already figured out how to solve by hand, but would rather not do ourselves anymore. Software testing is a good example. It's usually pretty straightforward for us as human beings to be given some software and to figure out how to test it. That's because we are the users of the software as well. But I say usually because there are actually lots and lots of ways and cases that make this much more difficult than we might otherwise think. But in the normal case, since we are users of software, we can just go about using software and seeing what happens as a way of testing it. But at this point, we run into various kinds of problems. First, we could start to get bored or tired. We could lose interest and make mistakes, ultimately making our testing itself poor quality. Which is an ironic thing because testing is supposed to be helping to determine the quality of something else. So how can it do that if it itself is not of the highest quality? Second, we could realize that we could never in a million years test a given piece of software. There might be too many variables to test, too many scenarios, or the software itself might be so slow that we can only run through a certain number of test cases before we grow old and perish. Third, we could have difficulties setting up an appropriate test environment. What if we want to test the software that powers an airplane? Do we need to become pilots ourselves in order to test it adequately? Or if we're not pilots, how do we set up a context where we can test the software? And fourth, we could realize that we don't understand the software well enough to test it. Airplane software is another good example. If I'm not a pilot, and in fact, if I'm not an aerospace engineer or something like that, how would I be able to determine if the software is even working correctly? There are all kinds of problems like these that we could run into. Automation can't help us with all of them, but it can help us with problems like the first problem, where we get bored and tired. If the steps we take to test a given piece of software or a given scenario are repetitive and simple enough for us to get bored, then maybe we can find a way to make a computer do those things instead of us. After all, software is just the flow of information specified as code or data, and so there should be a way to write other software to provoke and observe the app that we want to test for the purpose of testing it. Automation can also help us with situations like the second problem we mentioned, where there are just too many scenarios to test, or they take too long to test. Using automation, we can speed up the process of testing, as long as the techniques we use work faster than a human would. We can also usually scale up the number of automated testers much more easily than we can scale up the number of human testers, since the automated testers are just pieces of software. So these would be the main benefits of automation over manual testing. First, automation can reduce repetition or boredom by encoding the repetitive steps in software so that they don't need to be acted out by humans anymore. And second, automation can unlock a new level of speed or scale or reliability in testing. And obviously, all of this changes the role of humans in the testing process that used to test the software manually. Are these people still necessary anymore in this process? Does automation make testing so cheap and easy that we don't need human testers at all? Not exactly, I'd say. There are basically two ways in which humans are still very important, even in a world of automated testing. The first is that the whole business of automated testing still needs to be run by humans. At least for the time being, test cases are not automatically generating themselves, nor automated test scripts written by themselves. And this is being challenged today by work in the field of artificial intelligence for testing, and it's worth paying attention to developments in this field because there are approaches being explored right now that attempt to discover some aspects of application quality in a completely hands-off way by using AI testing bots. At the moment, these bots have somewhat limited scope and utility, but all this to say, for some time to come, human authoring of automated test cases is an important role, just as is human development of application software. The other way humans are important in testing is handling all the thinking that software cannot do for us. At the end of the day, software is written for humans to use, and humans must have some kind of input when it comes to judging quality, even if that input is minimal. There are also all kinds of cases that are difficult or non-obvious to consider, whether from a manual or an automated perspective. Choosing which scenarios to include in testing, for example, can be accomplished in conjunction with data and automation, but at the end of the day, it is an app team that has to make the call. All this to say, manual testing is not a practice which will ever completely disappear. It is one, however, which will adjust and probably narrow considerably. There is currently no reason, and in the future, there will be even less reason, for loads of humans to sit mindlessly tapping through the same scenarios just to test an app before launch. And ultimately, this is a good thing, because it frees up humans to do other kinds of work that is more creative. There will always be a place for humans in the process of developing tests and in the process of figuring out what to test and how to test it. It's a great idea to learn some of the most useful automation skills for app testing because I think these skills are currently useful and will be useful for some time yet. But remember that, as with any skill, it's important to keep it sharp and to keep an eye on developments in the field so that you can be a part of shaping the future of the industry. In this course, we're going to learn one specific tool used for web test automation called Selenium. But Selenium is not the only tool out there for web automation. So let's look briefly at a number of the tools that exist, and then discuss why we're working with Selenium specifically in this course. Here we can see a list of the tools, frameworks, or projects I'm going to describe. Just a note that my focus is on tools that are free and open source if possible. There are dozens of paid tools, which vary in quality and in features. But by and large, the use of web automation tools has moved into the open source arena. Selenium is by far the most popular, and it has always been open source. Also, I should say that this is necessarily a truncated list. I'm just trying to give you a sense of what's out there, and what you might explore beyond Selenium at some point, if there's a need. Currently, one of the most popular alternatives to Selenium is called Cypress. It's an interesting hybrid of an open source project and a paid product. It's designed to solve a bunch of pain points that people have had over the years with Selenium. And it does this by greatly restricting the contexts in which it can be used. Cypress is an all-in-one test runner, test framework, and automation API, and it comes with its own test running environment. You have to write Cypress tests in JavaScript, and the framework is designed in such a way to have tests live in the same codebase as your application code. Historically, Cypress has only supported Chrome, but early support for Edge and Firefox is now also available. Cypress works by injecting JavaScript into your web pages alongside your existing front-end app code. It also utilizes a special proxy server so that every web request the browser makes to your site gets trapped and rewritten to support Cypress's various features, like bootstrapping its own code or providing insight into the network requests made by your app. A tool that has a similar basic architecture to Cypress, but has its sights set on a much more narrow and specific set of goals, is Test Cafe. Test Cafe also uses a proxy server to inject JavaScript into web pages so that your tests have access to the page itself. It is not, however, its own test runner and test framework. It is a JavaScript-based automation library that you can install via npm and use in your own code however you like. One of its main selling points is that it supports any browser that exists or might exist in the future, since all it uses is plain old JavaScript and a proxy server that the browser has no special knowledge of and no special relationship with. Another browser automation tool that's been popular over the years is called Puppeteer. Puppeteer is maintained by Google and was originally developed as a way to automate a headless Chrome browser. What do I mean by headless? I mean a browser that is running invisibly on the system, without a full-fledged window that a user can interact with. Headless browsers have become very interesting to web testers over the years because they offer the promise of faithfully testing the browser without all the overhead of actually having to render web pages and so on, which can add a lot of time to the execution of tests. Google designed Puppeteer as a JavaScript library, so again, if you use Puppeteer to write tests, it means you're writing those tests in JavaScript. Puppeteer automates browsers by using something called the DevTools protocol, which is a non-standard debugging protocol that Chrome and all browsers based on the same codebase as Chrome support. The DevTools protocol is handled by a little server that sits inside the browser listening for external connections. We're going to learn more about clients and servers later on. We could write code that talks to this server and tells the browser to do things like execute arbitrary JavaScript, for example, or navigate to a certain URL. And this is basically all you need for most types of web page automation. So Puppeteer created a nice API on top of this DevTools protocol. Other tools have also been built on top of Puppeteer. For example, WebDriver IO, a Selenium and Appium client, is a Selenium client for JavaScript, but it has also implemented support for automating headless browsers more quickly by bringing Puppeteer to its automation library. Similar to Puppeteer is a newer project from Microsoft called Playwright. In fact, some of the key team that was building Puppeteer at Google moved over to Microsoft to work on Playwright. It has the same basic philosophy and design as Puppeteer, but it supports additional browsers, including Edge and Firefox. It does this by adding some code to those browsers, since they don't natively support the same DevTools protocol that Chromium does. At the end of the day, though, if you're using Playwright, you're using a JavaScript API very similar to Puppeteer, and you're using a debugging connection to get the browser to do things. The main selling point here is the ability to test headless browsers very quickly. Finally, let's talk about Robot Framework. This is a long-lived test automation framework that is not, strictly speaking, an automation library itself. Instead, it is a truly holistic framework with its own sort of natural language-based scripting language and test runner, reporter, and everything else that you would typically want in a test setup. It's designed to be easy for folks that aren't software engineers to use, if not to set up, since, strictly speaking, no programming is involved. Instead, test authors write declarative chunks of text that describe the conditions and expectations for a test. To actually make the automation happen, you need to choose one or more Robot Framework libraries, which are like little connectors that teach Robot Framework how to perform the automation steps you've outlined. There's a Selenium Robot Framework library, which is what most people use to do web testing with Robot Framework. So in this case, Robot Framework is not really an alternative to Selenium, but more of a different approach than the one I'm outlining in this course, even though Selenium is often still used with it. So, in this landscape of tools, why are we focusing on Selenium in this course? Well, we're going to talk a lot about what Selenium is shortly, so I won't go into too much detail now. But Selenium differs from all these other approaches in a few important respects. First, Selenium is built off of an official standard for web browsers. There's a standards group for the web called the World Wide Web Consortium, or the W3C. Over many years, Selenium's developers worked with the W3C to create something called the WebDriver protocol. It defines an API, a programming interface, that is exposed by all the major browsers, which allows native browser automation. When possible, I think it's a great idea to align with an industry standard. The chances that an industry standard will die off overnight are much smaller than the chances that one of these other projects will go away. Second, Selenium's architecture makes it possible to write tests not just in JavaScript, and not just in some specific text format, but in any programming language you want. This flexibility is super important for teams that aren't all using JavaScript. Personally, I think Python is a great language for test automation, from beginners to advanced practitioners, and using Selenium or Appium with Python is pretty straightforward. Third, Selenium's architecture also makes it easy for you to scale up your testing, which is an important aspect of a test environment that we'll discuss more later. Using Selenium, you can pay for browsers across the internet, or you can easily spin up your own and use a distributed computing model to run many tests at once. Finally, Selenium focuses on real web browsers run on real operating systems. This does make it slower in some respects than approaches which employ headless testing or other kinds of shortcuts, but it also makes it more faithful to the world you are actually trying to test. I want to be clear that there will never be one right answer to the question of which set of tools to use for testing. Many factors need to be taken into account. For example, the composition of the team that will build out the tests, the way the app is developed, the programming languages in use, the relationship between teams and responsibilities related to an app, and so on. Knowing how to use Selenium well is a key skill in the test automation industry. And whether you end up using it for a specific project or not, in my opinion, it's by far the best tool to be familiar with if you have to choose just one. So, let's keep learning about it. Mobile automation is a bit newer than web automation in general, but there have still been a whole slew of mobile automation tools released in the last decade. Most of them are not around any longer, and so thankfully we don't need to cover them. Appium is by far the most generally applicable and popular mobile automation testing tool, but it is not the only one. Just like we mentioned in the video on the landscape of web testing, choosing whether to use a given tool is a very context and situation-dependent process. Just because Appium is the most popular doesn't mean it will work the best in every situation. So it's good to understand a bit of the lay of the land and the advantages and disadvantages of each tool on offer. First, let's talk about XCUI Test. XCUI Test is a framework developed by Apple for the purpose of testing the user interface of iOS apps. It only works on iOS, so it is not a cross-platform framework. When you write code for XCUI tests, you write it in Objective-C or Swift, since those are the languages supported by Apple for iOS development. You typically write and run XCUI tests inside of Xcode, which is Apple's development environment, or IDE, for iOS development. Because Apple controls each piece of this equation, there is the possibility for some very nice integration between the IDE and the tests. There is a built-in test runner, and it's relatively straightforward to build and compile your tests alongside the latest version of your app, since the test code and the app code live together in the same codebase. XCUI Test exposes an API that gives us access to basic UI automation primitives, like finding elements, tapping them, performing basic gestures on the screen, and so on. The main advantages of XCUI Test are that it is officially supported by Apple and that it has great integration with Xcode. That's about it. There are some cloud test service vendors that support XCUI Test, so if you write your tests in this framework, you will have the option of running your tests at scale on several platforms. I should say one other thing about XCUI Test so it's in your mind for later, which is that Appium actually uses XCUI Test under the hood for Appium's own iOS automation support. So, in a sense, XCUI Test isn't really an alternative to Appium for iOS, though writing test code for XCUI Test directly is very different than using it from within Appium. But more on that later. Next, let's discuss Espresso. Espresso is an automation library from Google, designed to work with Android applications. Like XUI Test, it is single platform. Also, like XUI Test, it is designed to work well inside Google's official Android IDE called Android Studio. Espresso also gives us basic UI automation primitives, like finding views and performing actions on them. There are some more substantial differences between Espresso and XUI Test, however. First of all, Espresso tests must be written in either Java or Kotlin, because those are the languages that Google supports for Android development. Secondly, Espresso is built around a different method of UI testing. Tools like XUI Test or even Appium are often called black box automation tools because they force us as testers to think about the application as a black box. We can't see inside it. Now, an application is not actually a black box. A developer of the app has access to the source code, which highlights all the internal components and moving parts, so to speak, inside the app. But these internal elements are not visible to users. Users interact with applications from a black box perspective. To them, the app is all surface and no interior. Many UI testing frameworks take the same approach. And why not, since this is also how users interact with the app? Well, it turns out that by granting the test suite some access to the internal code methods or internal states of an application, you can sometimes make testing faster or more convenient. Test frameworks that provide access to application internal methods or functionality are called gray box frameworks. They can still interact with the app as a user would by finding elements and tapping on things, but they can also do things a user could never do, like trigger a specific function inside the app by its name in the source code. The designers of Espresso felt that by making it a gray box framework, they could avoid some of the common bad habits or bad experiences that can sometimes accompany black box UI tests. For example, since Espresso tests run at least partially inside your app as the app is running, they know when your app is busy working on something. So if your test code tries to, say, find or tap on a button at that precise moment, Espresso can tell that test command to hold on for a moment, wait for the app to finish its own business, and then allow the test command to proceed. This makes life easier on you as the test author, since you don't have to worry about being sure that the app is in an appropriate state for you to interact with it. One big drawback of this gray box approach is that you can't attach to just any old app and test it in this way. Because the Espresso tests have access to the app source code, they must be run on an app whose source code you have. You can't download an app from the Play Store and run an Espresso test on it, the way you could with Appium or UI Automator, which we'll talk about later. So Espresso has some pretty big advantages and disadvantages. The main advantages are that it is officially developed and supported by Google, that it has a tight integration with Android Studio for those already using it for app development, and that its gray box approach opens up doors for faster, more stable, and more convenient tests. Its main disadvantages are that it is single platform, must be written in one of two languages, requires tests to be bundled with the application source code to work, and can't automate anything outside of the application under test. So that's it for Espresso, except to say that, like XUI Test, Appium also has the ability to use Espresso for Android testing under the hood. Now let's turn to UI Automator. In a sense, UI Automator doesn't really need to be on this list. It's an older automation technology from Google. Google is now promoting and recommending that testers use Espresso. However, UI Automator, with its current version of 2, is still a useful tool to know about. It has many of the same characteristics as Espresso. It's produced by Google, only works on Android, and is designed to be written with Java or Kotlin. The main difference with UI Automator is that it is a traditional black box approach to UI testing. It doesn't know anything about your app or how your app differs from other apps that you might have downloaded from the Play Store. UI Automator is powered by the accessibility systems of the Android device. So all it knows about are UI elements and actions the user can take on the screen. One other important aspect of UI Automator 2 for our purposes in this course is that it is the technology which Appium uses under the hood for its standard Android support. What this means is that even if you use Appium, you may be using UI Automator 2 without knowing it. For this reason, it's good to know some of the facts we just shared about its capabilities, even if you never use it directly. Another popular automation technology, this time for iOS, is called Earl Grey. It has a name which is thematically quite similar to espresso in terms of caffeinated beverages, and that's no accident. Both espresso and Earl Grey were developed by Google. Earl Grey is Google's attempt to bring a technology like espresso to iOS. Because of this, many of the features of espresso that we discussed are also relevant to Earl Grey. Earl Grey is an iOS framework that you bundle with your application tests, which provides an API very similar to Espresso's for finding and interacting with views. Given that it is built as an iOS framework, you write tests in a similar way as with XCUI test, that is to say, inside Xcode, using the XCTest test case classes. The main benefits of Earl Grey are that, since it is bundled inside your application during your test, it can provide the same stability and activity synchronization features as Espresso. Similarly, Earl Grey is quite fast, and because it is hosted within your application, you also have access to your own app code, the way you would from a unit test. The main drawbacks are similar to Espresso as well. You can only write tests in Objective-C or Swift for a single mobile platform, and you're limited to testing apps whose source code you have. Earl Grey is not a general automation tool. It's really only for testing your specific app. However, you could theoretically combine Earl Grey and XCUI test in the same test suite in order to have some of the benefits of both at the same time. The last alternative mobile automation tool we'll look at is called Detox. Detox is the newest of all the frameworks we've discussed. It's designed to be especially useful in automating React Native apps, and in some ways is most closely related to the variety of JavaScript-based test frameworks we discussed in the landscape of web browser automation. Detox is a Node.js-based tool, and it requires that you write your tests in JavaScript. Detox works by building a bridge to Earl Grey for iOS and to Espresso for Android. For this reason, Detox isn't a fundamental automation technology and is similar to Appium in this way. Detox also has some nice boilerplate for integrating with your React Native app development and testing workflow. Detox's main benefits are the same as the ones offered by Earl Grey and Espresso: the speed and stability that come from graybox testing. And the limitations are more or less the same as well. You're forced to use just one programming language, and you're limited to testing apps whose source code you have, since the external frameworks need to be built in. Additionally, at this point, Detox only supports simulators and emulators, not real physical devices. The primary reason to use Detox would be if you're working on a React Native app and want all the tests as well as the app code to be in JavaScript. Okay, that's it for Detox. Of course, we need to say something about Appium, and we'll do that shortly in a unit dedicated to going into Appium's features and benefits as well as drawbacks. But what we should learn right now is that Appium is really more of a philosophical approach to solving the problem of mobile automation, rather than a fundamental automation technology. Don't get me wrong, there's an awful lot of code in Appium's codebase, and I wrote a lot of it myself. But the main job of Appium is to make other good automation technologies available in a usable package. As I've mentioned a few times in this unit, Appium actually uses technologies like XCUI Test, Espresso, and UI Automator 2 under the hood. So it doesn't, strictly speaking, compete with them on the level of automation technology. But hold on for a little bit, because we'll go into more detail about all of this soon. Okay, in this unit, we're going to talk about Selenium. What is Selenium? What is its history? What is it used for? And how does it work? Selenium was originally invented as a way to make things happen automatically on web pages. You can think of it like a robot that just knows how to make stuff happen on websites. You give the robot commands, similar to how you would tell someone else to look for a certain link on a page and click on it. Except this needed to be done using code. Someone named Jason Huggins developed Selenium at a place called ThoughtWorks, at first using JavaScript. It was a sort of spiritual precursor to what we now see in tools like Cypress today. Down the road, Selenium merged with a different project called WebDriver, which was being developed by Simon Stewart, who was also at ThoughtWorks. Well, what was special about WebDriver, and why did Selenium and WebDriver decide to merge? Well, Selenium, which at that point was called Selenium RC for remote control, had a number of limitations. The fact that it was powered by JavaScript inside of a web page meant that it couldn't do things that users could do with browsers outside the web page itself, like handle window alerts or work with native file upload dialogues. WebDriver had taken a different approach altogether and had written little bits of software it called drivers for each browser. They could control the browser on a much lower level. WebDriver also had a different idea for how users would write code to control it, which could open up control from a variety of programming languages and in a more organized way. Simon Stewart and Jason Huggins saw that each of their approaches had unique merit and thought the world would be better off if they joined forces, so they did. The official result was called Selenium WebDriver, although most people still just call it Selenium. That is more or less what we still have today, although the project has gone through many iterations, and the original JavaScript-powered component has been completely scrapped at this point in favor of the driver-based approach. Why do people use Selenium? Mostly as a way to test web applications. We can write code that looks very much like any old Python test code, except with Selenium as an imported library, we can control the operation of web browsers. Selenium is designed specifically for cross-browser testing, meaning that the same test code will work to run automation steps in any modern browser. You don't have to use Selenium for testing, though. You could use it for other automation purposes. Sometimes people use Selenium to automatically scrape data from websites that require a login, where a simple command line tool like curl or something might not cut it. This is not necessarily a good practice, and there are certainly lots of not great ways to use Selenium as well. So please be responsible with how you use any kind of automation, including Selenium. This situation, where we can use Selenium to automate any major browser, has come about through a lot of hard work over the years by the Selenium project contributors, as well as other folks that work at the companies that develop the browsers. A while back, it became clear that Selenium was important enough to the web development community that the standards group responsible for web standards decided to make WebDriver one of its official standards. This group, the standards group, is called the W3C, or the World Wide Web Consortium. And all the major browsers look to the W3C to decide how to implement things like HTML and CSS. It's great that a group like the W3C exists, because it's good for everyone that Safari, Firefox, Chrome, and Edge all render sites basically the same. It's a huge pain for developers and for users when different browsers do different things. And so the more we standardize, the easier everyone's life becomes. The same is true of web automation. When WebDriver became a W3C standard, it meant that every browser that wanted to be known as W3C compatible needed to produce its own WebDriver implementation. And that's exactly what happened. Today, you can download a driver produced by Google for Chrome, or a driver produced by Mozilla for Firefox, and they will both receive your WebDriver commands and do the exact same thing with them. This is great. So, what do you need to make use of Selenium? You need at least these 4 things. First, you need a computer with the browsers that you want to automate already installed, for example, Chrome or Firefox. If you don't have the browsers you want handy, you can use a cloud service to gain access to them, which is a topic we'll touch on later. Second, you need a driver for the browsers you want to automate. For Chrome, you need something called Chrome Driver. For Safari, you need something called Safari Driver. These are little programs you download from the various places that Google or Apple has specified and put on your computer so that they can be accessed from the command line. The driver is what controls the browser and is what speaks the WebDriver protocol so that you can send your test commands to it and have those commands actually be acted upon. All the other browser drivers work like this too. Third, you need a programming language that you will use to write your automation scripts. In this course, we're using Python, but you could use pretty much any other language like Java, C#, Ruby, JavaScript, or even PHP. Finally, you need a special Selenium client library corresponding to your language. Remember when we learned about Python modules, imports, and packages? In Python, the Selenium client is a package you can download and then import into your automation script. You then have access to all the browser automation commands through the imported module. We'll learn more about how this all works later, but basically, when you run your script in Python, or in whichever language you've chosen, your Python code gets translated into the WebDriver protocol and sent to the driver which controls the browser you're automating. So, that's a basic overview of what Selenium is. It's come a long way in the many years since it was first invented, all the way to now being an official web standard. And it helps thousands of developers and testers every day to ensure that their applications work well for their users. Let's talk about Appium in a little bit more depth. What is Appium? What's the story of Appium and how it came to be what it is? And how, generally speaking, does it work? How do you use it? Let's talk about all of these questions. First of all, what is Appium? Well, Appium is a number of things. Let's go through each of them. First, Appium is a mobile automation tool. You can think of it as being very analogous to Selenium. Selenium's purpose is to allow you to automate web browsers, and Appium's purpose is to allow you to automate mobile devices. Actually, Appium's purpose is bigger even than mobile devices. It certainly started out as a tool to automate mobile apps, but it has since broadened into a more generalized tool that aims to give you automation ability for all kinds of apps, regardless of platform. But for now, Appium is mostly known as a mobile device and mobile automation tool. Second, Appium is an open source project. Like Selenium, Appium has an open source license for its use, and a very permissive license at that, which means that anybody can use Appium for just about any purpose. You can go to GitHub and read Appium's source code yourself and extend it or contribute back to it. This is really important. Appium is different than tools like XCUI Test, which is developed behind closed doors at Apple, or even Espresso, which is technically open source as part of Android, but practically run as a closed source project by Google. Appium isn't owned by any mobile device platform or any testing company. It's owned by a nonprofit foundation called the OpenJS Foundation, which exists precisely to provide a neutral home for code. You don't have to worry about the whims of one company affecting a tool that you have integrated deeply into your development process. Third, Appium is a tool that wraps other fundamental automation tools in a WebDriver API. Here's what I mean by this. Appium does not have any code in it that tells iOS devices, for example, how to tap an element. It does not have any code in it which tells an Android device how to perform a swipe movement in an automated fashion. Now, this is a bit surprising, since isn't this the whole point of Appium, to do this kind of UI automation? Isn't Appium supposed to do these things? Well, yes and no. The fact is that there are already other tools which do this, like XCUI Test and Espresso, and which do it in a better way than the Appium team could do on its own. For example, Apple develops the XCUI Test framework to be tightly integrated with iOS. Apple's engineers write both iOS platform code and XCUI Test code. Who better than Apple to teach an iOS device how to tap on an element in an automated fashion? Likewise, who better than Google with their UI Automator 2 or Espresso frameworks to provide automation support for Android devices? The problem that Appium sees out there in the world isn't that automation tools don't exist. They do, and they're pretty much fine. Unfortunately, they put too many burdens on their users, in Appium's opinion. Appium would like to see the power and flexibility of the WebDriver API for mobile automation. And that's exactly what Appium's main role is: to take the existing automation technologies and make them available in a WebDriver interface, so you can write mobile test code that looks just like web test code and is based on industry standard APIs. Fourth, this choice of Appium to provide automation technology from within a WebDriver model means that you can write Appium tests in any programming language. This is a great benefit for many teams who might want to write tests in a language other than Objective-C or Swift for iOS or Java or Kotlin for Android. Fifth, Appium provides the same API for multiple platforms, which means that you can write test code that looks and feels more or less the same for both the Android and iOS versions of your app. In fact, if you design your test suite well, and if your apps work relatively similarly across both platforms, you can have test code that is exactly the same for both Android and iOS, with no duplication of code whatsoever. This is something which would be an impossibility if you used the native frameworks like XCUI Test and Espresso. Sixth, because Appium is open source, it has generated a huge community of practitioners, people who use Appium every day in their work. The result of this is that there is a lot of knowledge out there about how to get stuff done with Appium. There are Appium user forums, Appium chat groups, and lots of online guides to Appium out there, including my own set of articles and tutorials at appiumpro.com. So, how did Appium get to be this way? Let's look at a bit of Appium's history to learn more. Before there was anything called Appium, a QA manager at an online dating company in San Francisco had an idea. The manager was named Dan Cuellar, and his job was to ensure quality for the iOS app. He thought that surely there must be a way to automate the iOS app the same way we could already do with web browsers. he learned about a little tool from Apple called Instruments. Instruments was a standalone app you ran on a Mac. Dan discovered that within Instruments, there was the capability to type a snippet of JavaScript and then execute this snippet of JavaScript on an iOS device with a sort of automation API called UI automation. Dan took this idea with him to the Selenium user conference in 2012 in London and talked about this idea of his during a lightning talk. In it, he shared how he'd come up with a way to actually run this UI automation JavaScript code from outside the Instruments app, which was something Apple had never intended. This was the crucial insight that would open up the path to Appium, because when you no longer needed to manually open up a desktop app to run the automation code, you could have a fully scriptable automation environment. Some months later, Jason Huggins, who we remember from Selenium, was working for a testing company called Sauce Labs and wanted to find some solution for automating the iOS platform. He recalled Dan's demo at the Selenium conference because Jason was actually the one who had been chairing the lightning talks that day. So they got together and hatched a plan to take Dan's idea and make it something that worked a little more like WebDriver. It was an obvious thought for Jason because of his work on Selenium and WebDriver, and it was clear that what the world needed wasn't just mobile automation, but mobile automation that had the same advantages as Selenium. And what could be better than trying to use the same API to keep life easy for users? That's how the name Appium was born. Automation like Selenium, but for apps and not just websites. I happened to be a developer working at Sauce Labs at this time and got tapped to develop this Appium idea and turn it into reality. And that's what I did. I put together a small team, and together we implemented Appium's original iOS support based on Dan's original methods. I then added Android support, bringing Appium into the cross-platform world underneath the standard WebDriver API. The rest, as they say, is history, and there's an awful lot of it that we won't go into here. There have been many changes in Appium since that time, most notably the expansion of the Appium model to other platforms beyond iOS and Android, for example, Mac and Windows desktop platforms. But the basic idea has always been the same. Appium lets you automate your app in any programming language without requiring modifications to it and using standard APIs that thousands of developers already use for web automation. On top of all of this, Appium is open source, so you don't have to pay for it, and you don't have to be afraid that some company will go and do something nefarious with it for their own purposes. So, what features does Appium have exactly? What can you do with it? Well, many things. You have access to all the basic automation behaviors you'd expect from Selenium or any of the other mobile automation tools. You can find UI elements and interact with them. You can tap, enter text, swipe, and so on. Beyond that, Appium has implemented a whole host of helpful methods that go beyond the UI automation tools that Appium wraps, like XUI Test or UI Automator 2. Appium lets you, for example, send files to devices, take screenshots, videos from device screens, start and stop apps, and much more. There's a lot more to it, and you can always explore the Appium documentation to get a broader idea of what's supported. What do you need in order to use Appium successfully? Well, more or less exactly what you would need to use Selenium, with some additional steps and requirements, because there are additional requirements for the mobile development and test environments that go well beyond what's required for web development. Here are the things you'll need. First, you'll need a set, one or more, of virtual or real devices that you want to test on. Appium supports both virtual and real devices, though there are some limitations for both categories, which we'll go into more later. Just like with Selenium, if there are devices or platforms you don't have available locally, there are cloud services like HeadSpin or others that can give you remote access to them. Second, you'll need a mobile app development setup for each platform you want to automate. For iOS, this means Xcode and related tools. For Android, it means Android Studio, the Android SDKs, Java, and related tools. Third, you'll need Appium itself, which you can get in a variety of ways. Fourth, you'll need the appropriate Appium driver for the platform you want to automate. Once you have Appium, you can use it to download drivers without needing to go anywhere else to download them. Fifth, you'll need a programming language and a Selenium or Appium client library, just like we do for Selenium. So that's it. With all these pieces, you will be able to write automation scripts in your programming language of choice, starting up whichever apps you like, and automating them as if a little software robot were obeying your commands. Okay, that's enough of an overview of Appium for now. In this module, we are going to talk all about the WebDriver architecture. What is the WebDriver architecture? Basically, it's the conceptual underpinning of both Selenium and Appium. It's sort of like the skeleton of Selenium and Appium. Why not just move straight to learning how to use Selenium and Appium? My opinion is that knowing something about how Selenium and Appium work will put you in much better stead once you go to use them. It's kind of like driving a car or a motorbike. You can learn how to use them without knowing anything at all about how they work, and most people do. But what happens if something goes wrong? What happens if the car starts driving slowly, or you hear a grinding noise, or you start noticing some liquid pooling underneath the car? If you don't know anything about how cars work, you will immediately need to go and ask for help. And that's not a bad thing, of course. But my goal in this class is to give you solid footing for your whole test automation career. Knowing how Selenium and Appium work and what they have in common will make you much more effective, especially in moments where something isn't working as expected. Another reason to learn about the WebDriver architecture is that it is a well-designed architecture. It's one that you will likely start to see all over the place when you dig into other technologies. If you don't come from a software development background, especially web development, you might not be familiar with some of the names and concepts involved in learning this architecture. It is really important as you dig into automated testing that you also start to explore the surrounding areas of software development. Automated testing is software development, and you can gain many important insights that are relevant for your automated testing software by looking at the way other software is architected, designed. So you might be asking, what do we even mean by architecture in the first place? Well, it's very similar to how the word is used normally when we're talking about the design and construction of buildings. The architecture of a piece of software is the basic organizational structure. The way that the big moving pieces or various subcomponents are designed to relate to one another. It's typically easier to build software when you break the problem the software is trying to solve down into smaller chunks. And sometimes this leads to a software design where there are quasi-freestanding portions of the software that relate to one another. So when we talk about the WebDriver architecture, we're talking about the broad conceptual design of Selenium and Appium. We've already talked about a number of the pieces involved in this architecture, like drivers, Selenium libraries for particular programming languages, the W3C WebDriver protocol, and so on. And now it's time to dig into all of these in a bit more detail and see how they are related to one another. The first thing we need to understand about the WebDriver architecture is that it is a certain kind of structure known as a client-server architecture. What does this mean? It means that there are basically two main components in the architecture. One is called the client, and one is called the server. You could think of these as referring to different sorts of people you might find at a fancy French cafe. The client is the customer. In fact, client is the French word for customer. So that is why I am using the example of a French cafe. The customer comes in, sits down, and waits to be served. Someone needs to attend to the client. This person is called the server. Incidentally, this also works in French, since one of the names for a waiter or waitress is serveur or serveuse. So the server comes over and asks the client what they would like to eat or drink. The client gives the order, then the server goes away and eventually gets the food and drink and returns to give it to the client. What we have here is precisely a client-server architecture. We have one party, the client, that's asking for something, in this case food, which might involve various actions happening behind the scenes of the restaurant. And we have another party, the server, whose job it is to make sure those actions happen, and then to provide the correct response to the client, whether that response is food or information. Let's look at some examples. In this example, the client first says, "Hi, can I have a menu, please?" And the server goes back behind the counter, retrieves a menu, and brings it to the client. Now the client has a menu. In this case, the server hasn't caused anything to happen, really. All the server did is respond with some information. A similar example would be if the client had asked, "What's the soup du jour?" And the server responds with that information merely from their memory. In both cases, all that is being retrieved is information. In another example, the client could order some food, saying, "I'd like to have the steak frites, please." The server could take this request to the kitchen, to the chef, and then the chef would start working on the meal. In the process of working on the meal, certain things happen in the kitchen. Food is taken from refrigerators, quantities of ingredients are changed, and eventually a cooked meal is put on a plate. The server then brings that food back to the customer. In this example, the customer's request for steak frites resulted in something concrete for the customer. They got some food. But the difference now is that they also caused something to change in the kitchen. As a result of their request, there is now one less steak in the kitchen and fewer potatoes. In a final example, imagine that the client ordered a meal, and when the server brought it, discovered that the meal contained an ingredient to which the client was deathly allergic. The client might say, "Oh my goodness, get that meal out of here and throw it away, please." In this case, the server would take the meal back to the kitchen and put it in the trash, or maybe eat it themselves. That's what I would do, probably. Either way, the meal would soon be destroyed at the customer's request. We could think of lots of other examples of how the client and the server might relate, but the basic idea behind the client-server architecture is that you have one component, the client, which is requesting information or requesting that things happen, and another component, the server, which is making those things happen and retrieving the requested information. WebDriver is based on this same architecture. You have two main components, a WebDriver client and a WebDriver server. The client requests information about an app or a website, or instead of requesting information, might ask for some kind of action to take place within the app, like maybe a mouse click or a swipe. The server receives that request, makes the action happen by automating a browser or device, and returns any relevant information about the app or about the action that took place to the client. You might be asking yourself, why do we have this architecture at all? Couldn't the client and the server just be the same piece of software? And why have two components rather than just one? It's a great question, and it's true that it's not logically necessary for Selenium and Appium to adopt this client-server architecture. To use our French cafe example again, an individual person could run their own restaurant or cook their own food at home. But there are certain benefits to the restaurant model. With the restaurant model, food for many people can be stored in one kitchen and turned into meals on request. With the restaurant model, a client can call in an order even if they are halfway around the world. And with the restaurant model, people who all want to eat different things can sit and share a meal together. The same is true of the WebDriver architecture. Having a client-server model means that there can be many different types of clients who all talk to the server in their own idiosyncratic ways. We can have a client that's written in Java, so people that use Java can also use the Appium or Selenium server. We can have a client that is written in Python, so that people that use Python can use the same server. Rather than implementing Appium and Selenium many different times for many different programming languages, the client-server model allows a single Appium or Selenium server to service a variety of different languages. It also allows for Appium and Selenium servers and their attached devices and browsers to be located across the world from testers that use them. Because clients and servers can speak over the internet to one another, there is no restriction on where the client and server can be relative to one another. This creates a huge amount of flexibility for how Selenium and Appium can be used. It does, however, add complexity, and with any added complexity usually comes an added cost of time. The client and server do take time to communicate with one another, especially if they are very far away from one another on the internet. This means, depending on the structure of their relationship, the client-server architecture might be slower than a single component architecture. Still, the benefits of the flexibility we discussed outweigh the drawbacks of slowness, and there are usually ways to minimize any slowness due to the fact that the client and server have to talk to one another. One last point about the client-server architecture is important to comment on. In this architecture, for the communication between client and server to work correctly, the server has to be listening when the client makes its request. In our cafe example, this is equivalent to the restaurant needing to be open and one of the staff present to take orders. If the restaurant is not open, it won't do any good for the customer to come to the door and shout what they want. Likewise, you can imagine that the restaurant usually stays open for a long time and serves multiple clients while it's open. It's not as if the restaurant opens and closes its doors for each individual customer. So again, for all this communication to work, the server has to be up and listening, and then multiple clients can come in, make their requests, and leave. Okay, so that's all the basic idea behind the client-server architecture, and a little bit about why WebDriver servers like Appium and Selenium use this architecture. Now that we have discussed client-server architectures, let's discuss a specific kind of client-server architecture, known as a REST API. That's two totally separate abbreviations, REST and API, so let's break down each one. First, let's talk about the abbreviation API. It's a word I've mentioned a few times this course without really stopping to define it concretely. API stands for Application Programming Interface, and it refers to the way that some pieces of software allow themselves to be controlled by other pieces of software. A lot of software is built so that it can interoperate with other software. And why not? The whole point of software is to automate useful tasks. So allowing different pieces of software to talk to each other and to combine in interesting ways is a great and very natural idea. But just because we have two pieces of software that can be related in theory doesn't mean that they can talk to each other in practice. Let's take the example of financial trading software. You could imagine a web application that allows you to buy and sell stocks by clicking on drop-down menus, entering numbers into form fields, and clicking buttons to confirm your choices, just like you would use any other web application. This kind of software is really useful, certainly, and it's nice to be able to do these kinds of electronic trades using a website. But now imagine that you wanted to get into micro trading, and you had an idea for an algorithm that might require you to do hundreds or thousands of trades per second. The original software, the website, would not allow you to achieve this kind of frequency. There's no way that you, as a human being, can fill out a form manually that many times and that quickly. So what could we do instead to make this whole situation possible? Well, the company that runs the trading software could expose an API, an application programming interface. This API would define a standard way for other programs to interact with it, with the trading software. Then we could write our own software that we own that encodes our particular algorithm that we think is so great. And we can have our software use the trading software's API to make the trades happen at basically the speed of electrons. So there are many different ways that APIs can look. Whenever a bit of software exposes an API, it's up to that bit of software to design the API, to make it available, to document it, to determine what capabilities the API exposes, and basically to let everyone know how to hook up their own code to it. APIs can exist at the level of the internet, like our trading API example, or they can exist only between programs running on the same computer. So API, as a concept, is really just this generic idea of one piece of software defining a standard way for other pieces of software to interoperate with it programmatically. So now we're ready to talk about what a REST API is. Well, just by calling it a REST API, we know that it's some kind of API, some way for applications to allow other bits of software to use them. REST stands for Representational State Transfer, which is pretty opaque and not very easy to understand. So let's first of all say that REST APIs are APIs that are designed to work on the web. Web applications and web services often use REST APIs as the particular kind of API for working with those applications and services programmatically. Since the web is built on a data transfer protocol called HTTP, REST APIs are also defined to work over HTTP. Oh my goodness, another acronym, HTTP. What's that one all about? Well, HTTP is a really important acronym to know about, since it's the fundamental data transfer protocol for the web. It stands for Hypertext Transfer Protocol, and it's a system for computers to send text to each other over the internet. You probably recognize HTTP and HTTPS from the addresses of websites that start with HTTP:// or HTTPS://. HTTPS with the S at the end is just HTTP with all the text encrypted according to a security protocol. So everything I'm saying about HTTP is equally applicable to HTTPS. Okay, well, why do we need this communication protocol in the first place? Again, it's because for computers to talk to each other, there must be some absolutely well-defined standard for their communication. Computers aren't like human beings. We can still get the gist of what someone is saying, even if they or we use a few words incorrectly here and there. But for computer-to-computer communication, everything has to perfectly follow the rules. Otherwise, the computers will get confused. They don't actually have brains. They don't actually understand things. We just program them to act on data. So that data has to be completely well-defined in order for us to write programs to act on it. Essentially, HTTP is a protocol or a definition of communication that enables clients to request data from servers. Just like we talked about with the unit on client-server architectures. In the world of HTTP, there are clients who make requests to servers who potentially take their own actions and then respond to the client with some kind of text. An example could be your web browser trying to render the website example.com. It first asks for that from a server using HTTP, and the server responds appropriately in such a way that your browser can then display a web page to you. For this reason, there are two main components of HTTP. The request, which is what the client sends to the server, and the response, which is what the server sends back. A request is always directed to a certain host or server on the internet, either by its name or by something called an IP address, which is a kind of absolute way of referring to a particular server. The HTTP request has four basic parts. First, it has something called a method. We'll talk more about methods in a moment. For now, what we can say is that a method is basically a high-level description of the kind of action that this request is asking the server to take. Is this request asking for data? Or is it asking for the server to create a new object in the application? Or is it asking for the server to delete or destroy an object? That's what the method is designed to represent. Second, an HTTP request has something called a route. A route is like the address of something that the server should know about. A route is just a bunch of text with slashes in between bits of text to help with organization. Some examples of routes taken from my website appiumpro.com are maybe /additions, /additions114, or /contact. If you take any website that you visit in your browser and you strip off the HTTPS in front, and you strip off the domain name, like appiumpro.com, then whatever is left, starting with the slash, is the route. The route is included in the request to help the server know what kind of data to respond with. Should it respond with the home page, or a user's profile page, or your dashboard page, or a dynamically generated image? That's the kind of thing that's represented by the route. Third, an HTTP request has a set of what are called request headers. Request headers are a kind of metadata for the request that can encode lots of different information. It can tell a server what format the request data is in. It can tell the server what human language it would like a response back in. Requests can include any headers they want, and servers can support any headers they want. Fourth, every request has an optional message body. The message body contains information sent to the server along with the request to help the server do its job. If you enter some text into a field on a web page and then submit a form, that text all gets added to the message body and sent with an HTTP request to the server so that the server can save the text in a database or do whatever it needs to do with it. Now, let's talk a bit more about request methods. There are 9 HTTP methods in total, but since the WebDriver protocol only uses 3 methods, let's just look at what those 3 are. First, there is a method called get. Get requests are requests that are looking for information. They're not trying to make anything happen on the server or in the world. They're just trying to retrieve information without any side effects. If we ask the server in our French restaurant for the soup of the day, we're making a get request. Nothing is happening in the kitchen just because we asked about a menu item. We're just getting information. And since we're just getting information, get requests are not allowed to contain a message body. Second, there is a method called post. Post requests are typically defined as trying to create new objects on the application the server represents. So, if we are at the French restaurant and give our server an order for steak frites, then we are essentially making a post request. What we have done is create a new order that will show up on a slip of paper or on a screen in the kitchen. That order is an abstract object managed by the restaurant. It might have its own properties, like the customer name or the table number, the different meals that compose it, and what stage of production it's in. Since post requests typically create something new on the server or cause some kind of action to occur on the server that might have effects and consequences, post requests are allowed to send a text-based message body that the server can read so it knows exactly how to fulfill the request for the action. Third, there is a method called delete. Delete requests are meant to signal to the server that an object should be destroyed. Imagine that we had previously phoned into the French restaurant and made a reservation for 2 at 6 o'clock tonight. That would have been another example of a post request, where we are asking the server to create a new reservation object, which contains our name, our party size, a date, maybe a time. Now imagine that we need to cancel our reservation because we're so excited about learning HTTP that we decided to just order pizza at home. So if we call and cancel our reservation, that's equivalent to making a delete request to the restaurant. We're telling the restaurant, hey, destroy that reservation that we made earlier. It's no longer valid. So these are the HTTP methods that we care about for the purposes of the WebDriver protocol and this course. So now let's keep going with our French cafe example and start to imagine what it would be like to interact with this cafe over HTTP instead of just talking to a server, a human server, face to face. Well, we could imagine that the cafe hosts a web application, maybe at frenchcafe.com. And this is not a real site, so don't bother going there. Then we could imagine constructing an HTTP request that looks something like this. In this example, we are constructing a GET request to the route /soup du jour and sending it to the frenchcafe.com host. Notice that we also always include the version of HTTP we're using. But that's the same for every single request, which is why I didn't mention it earlier. We just need to put that string HTTP / and then the version of HTTP. I picked 1.1 for this example. Now, if the server is configured in such a way that it knows how to respond to this request for the /soup du jour route, we will get back a response containing the soup of the day. But we don't yet know about HTTP responses. So let's talk a bit about that first, so we can see what kind of thing the server might respond with. HTTP responses are what the server sends back to the client after it has finished handling a request. While it's handling a request, the client is just sitting there waiting for it, just like a customer sits and waits at a restaurant table when they have made a request. It's not like those phone systems where you call a customer service number and they record your number so they can call you back when things are ready. If you leave the restaurant, the server has no way of contacting you and telling you your food is ready. So with HTTP, the client just stays on the line until the response has come back. And if it doesn't, it will never receive that response. Like HTTP requests, responses have a number of parts. There are three main parts. First, an HTTP response, status code, and status message. These tell the client generally what sort of thing happened on the server when it tried to handle the client's request. There are dozens of different status codes, but here are a couple examples to give you a flavor of the kind of things they can mean. We have 200 code and a message of OK. This code and message combined means that the request was handled successfully with no error or confusion on the part of the server. Another response could involve a code of 404 and the message not found. This response would mean that the server didn't find any resource or wasn't able to handle the route provided in the request. I know we've all seen this at one point or another while browsing the web, trying to access a certain URL. We could also have 500 internal server error. A 500 code means that something went wrong inside the server. As far as the server knows, your request was valid, but when it tried to handle it, it encountered some kind of internal error. It could be a bug in the server code or any number of other problems. A 501 code means that the combination of request method and request route were not able to be handled by the server because it explicitly and specifically doesn't implement support for that combination. The implication is that it will probably implement support for it at some point in the future. Otherwise, it would normally return a 404. Second, like the request, the response can contain any number of response headers. These are just like request headers in that they are basically metadata about the response. One common response header is, for example, the date header, which specifies the date and time at which the response was constructed on the server. Third, the response can contain a message body with arbitrary text. This is how the server sends information back to the client. That information can be in any format as long as it's text. It might be HTML, which is how servers send back web pages to be rendered by the browser. It might be text. It might be in some other structured format like YAML or JSON, which are two common text-based data formats used around the web. So, with all that in mind, let's imagine what a response from the FrenchCafe.com server might look like to our request for the soup du jour route. Here's our response. It reads HTTP/1.1 200 OK, content-type, text plain, charset equals UTF-8, and then some text, a really nice French onion soup with croutons. Let's parse this out. In this response, we start out with the version of HTTP, as always, so that different systems know how to parse the response format, in case the format changes in future versions of HTTP. Then we have the status code and status message. In our example, we include a header called content type, which tells the client what format the response message is in. In our case, it's plain text, using a specific kind of character set known as UTF-8, which is one of the standard character sets used for encoding text on the web. After the mandatory blank line that you see, we have the response body, which is just some text describing the soup of the day. Okay, that's about it for HTTP. And now that we're all experts on it, let's circle back to REST APIs, where we departed our conversation earlier. I said earlier that REST APIs are a certain kind of API protocol built using HTTP. So what's special about REST? Well, REST is basically a set of patterns for using HTTP that attempt to encode information about objects and what sorts of interactions we can take with them. When I'm talking about objects, I mean objects that exist on the server that could represent various kinds of application logic or objects. For example, orders or reservations, as we talked about earlier. One important observation about HTTP is that it is stateless. What does stateless mean? It means that in between different requests, the client and server are not connected. They don't have a long-running conversational memory. Imagine that the server in our French cafe is so absent-minded and forgetful that after they help us with one request, they completely forget who we are and everything that we've already asked for. So if we order the soup of the day, that's great. The server will go and place the order for us, as we see on the slide here. But let's say we flag down the server 10 minutes later, completely different conversation, and ask, how's the soup coming? Why isn't it ready yet? Then the server would reply, what soup? And in fact, who are you? Would you like to order something? HTTP is kind of like that. Conversations between the client and server over HTTP are really just a series of completely independent experiences. They don't take place in any larger context, unless they both find ways to establish that context on each side. So let's imagine how this idea of establishing context on both sides would work with our amnesiac French cafe server. To get around their forgetfulness, the restaurant and its clients could establish a system where each order is given a unique number. So when I place my order for the soup du jour, the server takes the order to the kitchen, and it's the kitchen's job to assign it a special, unique number. Then the server brings me back that number and says, here is your order number. Please keep it handy for any future queries about this order, because once I leave your table, I will forget everything about you and your order. So, now that we have the order number, when we flag down the server in the future, we don't need to rely on their memory, which doesn't exist. Instead, we can say, can you tell me the status of order 42? Then the server can take the number 42 to the kitchen, and the kitchen can check on the status of the order, which has that number. And finally, the server can come back to me with the status before they have a chance to forget who I am. It's all part of the same interaction, so their memory suffices for that one interaction. What's going on here is that both the restaurant and the client want to have a long-running conversation about the same object, the soup order. But because the means of communication, namely the waiter, has no memory, the restaurant and the client both agree to keep a simple reference to the object in the form of a number that can easily be used to identify the order on either side. And this is exactly why we have the word representational in the acronym REST. Because REST APIs use some kind of token or unique identifier to represent objects that both the client and the server want to work with. And those representations are included in each request and response, so that the client and server know what they are communicating about, even over many different completely independent HTTP requests. So let's put everything together with a look at what a REST API for FrenchCafe.com food orders might look like. Let's assume that we have a route called /orders that will allow us both to place an order and to check its status. So first of all, we need to place an order by making a request. It's going to be a post request because we're telling the restaurant to create a new object in the kitchen, namely our order. So here's our request. And in it, we are making a post request to the /orders route, as we mentioned. And we are including a content type header to tell the server that the request body we are sending is in a special format. The format is called JSON, standing for JavaScript Object Notation, JSON, which is a special way of creating structured text. You can see an example of it in the message body itself, where we have some labels and some values that correspond to those labels. The first label is called menu item, and its value is a special string denoting the soup of the day. We also probably want to include which table this order is for. So let's say it's for table 15. Now, when the server receives this request, it creates an order in the kitchen and starts work on the soup. But it needs to respond to us with something that will let us refer to the soup later on. In other words, will let us represent it in an easy way. So let's say the kitchen decides that the order number for this order is 42. It can create a new slip of paper or order in its database with that number as its identifier. Then it can respond to us as follows. HTTP/1.1, 200 OK, content type application/JSON, and then we have some JSON text here. In this example, the server is responding with JSON formatted text, just like we did in the request. Again, the request and response format does not have to be JSON. It's just whatever the server defines in its API. But as a matter of fact, many servers do use JSON, and the reason I'm using it here is because Appium and Selenium use JSON for everything as well. So you can see that what is returned as the response body is a JSON representation of the fact that our order now has an ID of 42. Orders also have a status, and so when a new order is created, we can pretend it gets a status called new. Now, let's then imagine that 10 minutes have passed and we want to check in on our order. How can we do that? Well, first, let's construct a new request, this time using our special order ID to figure out what exactly is going on. This time, we need a GET request because we're not trying to make another order. We're just trying to get information about an existing order. We're not trying to make anything happen in the kitchen. In other words, we just want to know what's going on. The magic here is all in the route. Notice that after /orders, we've added /42. Why do we do this? Well, since we have a GET request, we can't include any data in the request body because GET requests aren't allowed to have bodies. But somehow we need to tell the server what the ID of our order is. Otherwise, the server won't know which order to give us a status response for. So we can imagine that the server knows how to handle a route where the last item in that route is an order ID, just like we have here. So when the server receives this request, it can use its own programming to parse out that number 42, look up the order based on that number, determine what's happening in the kitchen, and then return a new response. So you can see that we get back the same type of response as before, but now we can see that its status property has been updated. It turns out our soup is ready, so it should be out soon. This is a great example of how REST APIs work, by ensuring that server objects can be represented by simple text tokens. It makes it easy for the client and server to have conversations about the same objects. Now, why did we go into all this detail on REST APIs? Because this is exactly how Selenium and Appium work. This is exactly how the WebDriver protocol is defined. When you automate a web browser or a mobile app, you are interested in certain objects on the screen, like elements or windows. And using a REST API allows the Appium and Selenium servers to maintain a reference to those objects. That reference can be shared with the test script itself. And that's exactly what we'll look at in the next unit, which will go into much more detail on the specifics of the WebDriver protocol. Okay, we've already looked at a bunch of the fundamental concepts we need to understand the WebDriver protocol. And this is the API that both Appium and Selenium expose. Earlier, we saw how HTTP and REST APIs can be used to allow clients and servers to interact over the internet by aligning their communication and standardizing it around ways of representing objects they both care about. In our case, Selenium and Appium act as the server in the client-server architecture, and the test script acts as the client. So the client decides what should happen, and the server receives a series of requests in order to be told what should happen, and then to actually perform the requested behavior and return any relevant information back as a response. Again, the specific format for this conversation is called the WebDriver protocol. Here's a definition of the WebDriver protocol I think we're now in a position to understand. The WebDriver protocol is an object-oriented browser automation API exposed over HTTP using REST principles. So the first question is, given that the WebDriver protocol is object-oriented, what are the objects that it knows about? The first object in the WebDriver API is called a session. A session is basically a single instance of automating a certain browser or device. Going back to our really fun example of the French cafe, we could imagine a session as a single visit to the restaurant. You go to the restaurant and are given a table to sit at. And that table is yours for the duration of your meal. You might have any number of requests to the kitchen over the course of a dinner, but at some point you pay and leave. That is the equivalent of a session for Appium and Selenium. With Selenium, when you start a session, you're given a browser to automate. And when you're done automating that browser, however long you've used it, you tell Selenium that you're done, and it closes the browser for you. That ends your session. Similarly, with Appium, when you start a session, Appium reserves a device for you, and you can automate that device until you declare that you're done. That ends your session. So, the first object that both the client and server care about is a session. The second one is called an element. An element represents a UI element, a user interface element, present on a web page or on the screen of a mobile app. You create element objects in the Appium or Selenium server by first finding them using the session object. Once element objects are created, in other words, found, you use those objects to perform various interactions with those elements. So sessions and elements are the two main objects within the WebDriver protocol that get their own special IDs as representations that are shared between client and server. There are other conceptual objects which work similarly, but which aren't necessarily given the same special treatment in the structure of the API. For example, a third object available to work with in the API is the window object. And this, understandably, is used mostly in web automation with Selenium and not for Appium, since mobile apps tend not to have multiple windows the way browsers do. But by asking Selenium which windows are present, you can retrieve IDs for window objects and work with them to do different actions, like closing a window, for example. A fourth object is the cookie object. Cookies are little bits of data that web browsers send as part of the request header to websites. These bits of data enable the website to learn something about who is making the request. It's how websites remember who you are from request to request, because remember, HTTP sessions are stateless. Selenium allows you to get and set cookie details, as well as add and delete cookies entirely, again, all by using a reference to the cookie object through the API. Now, cookies already have their own names, so these are the IDs which are used, just the name of the cookie. So, given this variety of objects, we can then begin to map out the various features expressed in the WebDriver protocol by asking which actions or which commands are available on each of the session and element objects. Let's look at just a few examples. Okay, let's look at commands that are available on the session object. First of all, if you have a session object, you can always choose to end the session using that object. You could use the session object to send a web browser to a certain URL to cause it to load that page. You could trigger back, forward behaviors in a browser or device, or refresh a web page as well. Fourth, you can get the title of a web page. You can also find specific HTML or UI elements using various criteria that help specify the element or elements you want to find. You can generate complex touch actions or gestures on the web page or within a mobile app. You can get a list of which windows are open. You can open a new window or close an open window. Additionally, you could get a list of the cookies, as we talked about earlier. You could add a cookie or delete a cookie, and more. In other words, these are examples of high-level actions that take place within the website or the app as a whole, which is why these actions are available on the session object. Now, imagine we have an element object that we've retrieved by finding a UI element using the session object. Let's look at some of the things you can do once you have this element object. First, you could click that element, which translates to a tap for mobile applications. Secondly, you can get any text which is displayed on or within the element. If the element is an input field of some kind, you can type text into it. Or you could read various element attributes. These might be invisible to the user, but might form a part of the HTML document, for example, CSS properties, and so on. So this is basically the structure of the WebDriver protocol in a nutshell. You have these handful of objects, sessions, elements, and so on, representing aspects of the user interface, and you have commands that are associated with each of those objects. Again, this is what it means for the WebDriver protocol to be object-oriented. Now, as we think about each of the commands that are a part of the WebDriver protocol, like navigating to a certain URL, or finding an element, or clicking an element, we can observe that not all commands work exactly the same way. Some commands are used to retrieve information from the browser or device, for example, requesting the title of the currently loaded web page. Other commands make things happen, like clicking or performing some kind of touch action. And some commands need additional information to work properly. For example, the command that's used to type text into an input field is called element send keys in the protocol. And for this command to work properly, there needs to be a way for the test author to say exactly which text should be sent in as a series of keystrokes. In other words, this is a command that takes a parameter. It won't work unless you provide the additional information, namely which text to send, to direct Selenium or Appium in exactly how to fulfill your request. So, some commands have parameters and some don't. Likewise, commands can vary in the kind of responses that are delivered back to the client. Some commands don't really need to send any particular response back. When you click on an element, for example, there's really no information that needs to come back, other than the assurance that the click actually happened. Other commands, however, are only useful when they send information back. The command to get the title of a web page, for example, is only useful if it can return arbitrary text back to the client, since web page titles can be pretty much anything. So, when it comes to responses, we really have two categories of data in the response. First, we need some kind of indication of whether the command was successful or not. If the command wasn't successful, what kind of error was encountered, and so on. This type of response data applies equally to every single command. Second, for some commands, but not all, we need arbitrary data to be returned, which might differ based on the nature of the command. If we're talking about the getTitle command, then we need a text string to come back, because that's what a title is, a string of text. If we're talking about the getWindowHandles command, which tells us about all the windows that are open and attempts to give us an identifier for each window, then we actually need a list of strings to be the response of the command. In sum, each particular command needs to define what sort of parameters it expects, if any, what sort of response it will provide, if any, and also what errors might potentially result, so that it can return the appropriate error response if an error does occur. Okay, now you know pretty much everything about the WebDriver protocol except for the specifics of what it looks like. So let's dig into some of those specifics. But first of all, every command the protocol supports is specified as a combination of an HTTP method and a server route. So a combination of an HTTP post request and the server route /session means that we want to execute the command called new session. We usually just write this as post/session, even though in the actual HTTP request body, it would look different. What does the new session command do? Well, it starts a browser or a mobile app for you and makes sure that everything is ready to automate. It might also lock the browser or device so that no other sessions can be started on it. How does the new session command know what kind of browser or mobile app you want to automate? Well, you need to tell it by passing in some information in the HTTP request body. If you look at the specification for the new session command in the official WebDriver documents, you will see that it requires a special kind of parameter, encoded as a JSON object. Here's an example of what this JSON object could look like. In the WebDriver protocol's terminology, this is called a capabilities object, because you're using it to essentially tell Appium or Selenium what capabilities you would like your session to have in order to know that you're automating the right sort of thing. And this bit of text is formatted according to the rules of JSON, which uses curly brackets to create sets of keys and values. It's basically a way of storing labeled structured data. In this case, the main JSON object has one property, one key, one label. We can use all of these words to describe the string capabilities. The value for this capabilities key is itself another JSON object, denoted by the opening of another set of curly braces. This inner object has two properties, or keys: always match and first match. And notice how they're separated by a comma, which is how you specify that there are more than one property or value in your JSON object. Let's ignore the difference between always match and first match for a moment, because they're not essential for our understanding of what's happening here. Let's focus instead on what's inside the always match value. This is a third layer of the object, another object itself, and it has three properties. If you look at these keys and values, it should be pretty clear what they represent. The three keys I'm talking about are browser name, browser version, and platform name. Together, they mean that we are requesting a new session that supports a particular browser, in this case Firefox, a particular version of that browser, in this case 79, and running on a particular operating system, in this case Mac OS. The values for those keys specify exactly which ones we care about. In sum, this capabilities object is telling Appium or Selenium that we want to automate Firefox 79 on a Mac OS computer. So in order to make that actually happen, what we need to do is construct an HTTP post request to the /session endpoint, sending the capabilities JSON object as the message body. We can do this any way that we want, either from code using a programming language, or by hand, so to speak, using a command line utility. So long as we have an Appium or Selenium server that's listening for requests, and so long as we follow the rules in how we put the HTTP request together, it will work. Ultimately, the HTTP request should look something like this, where we have all of the pieces, the HTTP method, which is post, the HTTP route, which is /session, a content type header, which tells the server that we are sending JSON formatted text, and then the message body itself, which is just the JSON object we saw earlier. If we send this to a Selenium server, it will know that we are trying to start a session because we are speaking the WebDriver protocol. We're following the rules of the API that it has defined. Okay, great. So that's how we would use the raw WebDriver protocol over HTTP to start a new session. But once the session is started, how does the server respond? And what does the server respond with? Well, there are two cases here. Either the server successfully started the session, and so there is now a session object stored within the server, or there was an error starting the session, and so the server needs to communicate that something didn't work right. There are lots of reasons that an error might have occurred starting the session. Maybe the capabilities you provided don't match any browsers or devices that the server knows about, for example. But let's first imagine that the session is created successfully. In this case, the HTTP response would look like this. Since we learned all about HTTP recently, we have the power to decode this. What's happening is that the server is sending back a response with a status code of 200, meaning everything went just fine. We have a response header here too, letting us know that the content type of the response is JSON, just like the content type of the request was. This is an important point. The entire WebDriver protocol requires that JSON be used in both request bodies and response bodies. It's a good way to ensure a standard for encoding and decoding data that flows between the client and the server. And now let's look specifically at the response body. It is a JSON object which has one key, namely value. The value of this key is itself a JSON object containing two keys of its own. The first is session ID and the second is capabilities. Let's discuss capabilities first, since it should look pretty familiar. In fact, it's exactly what we sent in to the server. And in many cases, that's exactly what will happen. Essentially, capabilities will be returned here as a way for the server to tell the client what capabilities it actually ended up using in starting the session. But the essential part of this response object is the value of the session ID key. It's a single string with a bunch of random letters, numbers, dashes, and so on. It could be anything, and that is exactly the point. The session ID is the token that the server has decided to use to refer to the session object it just created for the client's automation commands. In our discussion of REST APIs, we talked about how these unique identifiers are used to share state between the client and server. With this little ID that can be passed around, both the client and the server can be sure they are working with the same object. In this case, the same session. The idea is that as the client, we take this ID and save it so that we can use it anytime in the future we need to run a command using this particular session. Now let's look at another command so we have an example of how to use a session ID for a session that we've started. The command we're going to discuss is called findElement, and it's an extremely important command since it is what lets us find and ultimately interact with UI elements, and this forms the basis of our apps and of our testing. If we read the W3C WebDriver specification, we learn three things about this command which are essential for using it. First, the findElement command requires the use of an HTTP post method. Second, the findElement command exists at the route /session /session ID inside some curly braces /element. Third, the findElement command requires a JSON object parameter that has two keys, using and value. Let's discuss each of these things in a little bit more detail. We have a post method here, which is a little strange, perhaps. Presumably, we are just getting a reference to an element. And in that case, you'd think we're just retrieving information, not creating any kind of change to happen on the server. But there are two reasons this is a post method and not a get method. The first reason is that although getting a reference to an element doesn't theoretically cause any changes on the website or the app under test, it does actually cause a change in the server. Going back to our French cafe example from an earlier unit, if we create an order of some food for the kitchen, we use post because a new order object has created, even though no actual food has yet been handled. The second reason we have a post method here is because this command requires parameters to be sent in. And it's a bit tricky to encode lots of parameters for a GET request, since GET requests are not allowed to have request bodies. Okay, the next thing to discuss is the route. This route looks a little odd. It has these curly braces in it with the word session ID inside. What this means is that there is a slot in the route where instead of writing the words session ID in braces, we should actually put a real session ID, which we've gotten from the server before, through a call to the new session command. This is exactly how we talked about using IDs to refer to objects, so that the client and server can maintain a conversation about the same things, even though each request and response happens in isolation. The third part of the specification for this command's request is the set of request parameters. We have two required parameters, which must be sent together as a JSON object. These two parameters are called using and value. We'll talk more about what these mean when it comes time to find elements with Appium and Selenium. But for now, we can say that the using parameter refers to the way that we want Appium or Selenium to find an element, and the value parameter refers to some property of the specific element that we want to find, which will help us find that particular element and not any others. So let's construct an HTTP request based on all of these things. If we assume that we have a running session with the ID that we got back in the new session example earlier, then we can construct a find element request like this. First, we specify that it's a post request. Then we construct the route based on the template defined by the command. It looks like /session, then another slash, followed by the actual session ID for the current session, finally followed by another slash and the word element. We set a content type of application/JSON since we're sending JSON data. And the JSON data itself has two keys, using and value. In this example, the value of the using key is CSS selector. This means we are going to send the server a CSS selector and ask it to find the first element that matches that CSS selector. The actual CSS selector we are sending in is submit form with the # in front of it, which is just a way of specifying a particular element in the HTML of a website, namely the element whose ID is submit form. Of course, it's up to me to know that the particular website I'm automating has an element with that ID for me to find. So what happens if Selenium or Appium finds an element that matches a request like this? Well, it will send back an HTTP response. We're imagining in this case that there was no error, and so the status code and message are 200 OK. We have our standard content type header of application/JSON with the character set noted. And the response value object has a single property inside the value, namely element-606-11E4-A52E-4F735466CECF. What on earth is this doing as a property name? It seems to make no sense whatsoever. Well, it's actually just a hard-coded, never-changing, quasi-random string that basically just means that its value, whatever comes after the colon, is going to be the ID of an element that was found by the request. So hold on a minute. Why use this very strange string as a property? Why not just use a key or property name like element or element ID? And that's a very good question. The answer has to do with some complicated facts about how WebDriver lets you execute arbitrary JavaScript inside a web page. But we won't go into a detailed explanation of that right now. In fact, after this course, you'll never need to worry about this property again. It's not something you ever see during the course of your testing. So we can safely ignore all of the reasons that it is what it is. So back to our earlier discussion. The value of this very weird property is just a string. It's an ID, just like we saw with the session ID earlier. This time, it's an ID that refers not to a session object, but to an element object. What has happened when you found an element is that the server has gotten a hold of that element as an actual element object. But now it needs some way to refer to that element so that the client and the server can keep a conversation going about that element down the road. So again, we use a more or less random ID that has been assigned to this element as its name tag, so to speak. And that's what's returned to the client. We need to use this ID for future requests to do something with this element, like tap it or click it, just like we used the session ID in this request to find an element. Okay, that's a lot, but we're not even totally done with this example yet. What happens if the element you ask for can't be found for one reason or another? What if there is no element with the CSS selector of submit form? In that case, the Appium or Selenium server will respond with an error response. An error response is a type of WebDriver protocol response that is mostly the same as a normal response, but differs in two ways. First, it differs in that it will return an HTTP status code that is not 200. The exact status code that will be returned will depend on the precise error encountered. In our example of finding an element, if the element isn't found, then the status code returned will be 404, which is exactly what web servers are supposed to return if they cannot find a resource which has been requested. Second, an error response differs from a normal one in that the JSON object returned will have as the value of the response a special format with a helpful message saying something more about the error. So let's look at an example. If the server could not find the element we requested previously, then it could respond with something like this. This HTTP response has a 404 status code and the status message not found. That tells the client straight away that something hasn't gone as expected. And then the value object provided in the response body has some more information. There is an error field which contains a short string saying exactly what couldn't be found. Then there is a message field which can contain a longer and more dynamic string with more complete information if necessary. There could also be a stack trace field that helps users understand where in the server the error was encountered, but that's not relevant for this example. You might be wondering, what sorts of errors does the WebDriver protocol know about? There are almost 30 of them, in fact. Each one is defined by an HTTP status code, which might be 404 as we just saw, or it might be something else like 500. But the status code isn't enough to pinpoint which error we just encountered. For that, we also need the error string, like no such element. Other errors have strings like no such alert, or invalid argument, or even a catch-all error, unknown error. You can see the full list in the W3C WebDriver specification. Okay, we've covered a lot so far in terms of learning the WebDriver protocol from the ground up. We've talked about commands, how they work with different objects, how they have their own specific sets of parameters and responses, and how it all gets implemented on the level of HTTP requests and responses. So let's close by looking at a select list of a few more commands and how they are defined. First, we have the element click command. It is called by submitting a post request to the route /session/session ID /element ID /click. Notice how, for this command to work, we have to have an ID for both a session object and an element object. This requirement represents the reality that to click on an element, we first have to have a browser or app open, and we secondly need to have located the element we want to click. This command doesn't take any parameters, and it doesn't have any response values to speak of. Second, we have the element send keys command. It is called by submitting a post request to the route /session/session ID /element ID /value. Are you seeing the pattern here? Every command which involves performing an action on an element has a route which is based off of the /element route. This design of the routes indicates clearly the objects that are available in the WebDriver protocol and how they are structured. This send keys command does take a parameter, however, since the server needs to know what keystrokes you want to send to an element. The single JSON object field required is called text, and the value should be whatever text you want to show up in the element. Third, we have the getElementText command. It is called by submitting a GET request to the route session ID, element ID, finally /text. This time, we use a GET request with no parameters because we simply want the server to return to us the text which the element is currently displaying. We're just asking for information. The response we get back will have the text string as the response value, so we can do whatever we want with it. Finally, we have another very important command, which is used to end a session that we are done using. It's always important to end sessions cleanly, even if an error occurs on the client side of the equation, and we don't need to do any more automation. Ending a session tells Appium or Selenium that it's okay to reset the state of a browser or device, or close things down, or make resources available for future tests. We call this command by submitting an HTTP delete request. This is one of only a few commands in the whole protocol which is defined as using a delete HTTP method. For the route, we simply need to use /session/session ID, since this refers to the session object. Once we do this, the session will end and we'll be all set. Okay, that's it for the WebDriver protocol. There are many, many more commands than we covered here, but with these few examples, you've learned pretty much everything that it's possible to learn about the structure of the protocol. This will make it much easier to understand what is happening in the course of running Selenium and Appium commands, and will help you to troubleshoot any issues you run into down the road. At this point in the course, we've learned all about the WebDriver protocol and how it encodes browser and element objects and the actions you can take with them as an HTTP-based API. The WebDriver protocol was developed by the Selenium project team in conjunction with the W3C standards group and members of the various companies that produce the web browsers mostly we all use, like Google, Apple, Mozilla, and so on. Their whole purpose was to come up with an automation API for web browsers and web applications. They obviously were aware of non-web apps like mobile device apps, but their focus was not on building an automation API for anything other than web browsers. What this means is that as you look at the list of commands available in the WebDriver API, you'll find only commands that are relevant for testing websites. But what about mobile apps? Is the WebDriver protocol sufficient for everything we want to do for automating mobile apps? Well, it certainly gets us a lot of the way there. Much of the WebDriver protocol isn't limited conceptually to websites. Both websites and mobile apps have user interfaces that are based around interacting with elements. But some parts of the WebDriver protocol really only make sense when it comes to websites. Getting the URL of the current page, for example, is not an action that makes any sense when using the weather app on your phone. Likewise, mobile apps rely on various technologies that don't exist in web browsers at all. For example, you can control some mobile apps by turning the device in various directions, relying on an internal accelerometer to give the app information about the device's state, or more boringly perhaps, devices usually have some kind of home button or other action you can do to return to the home screen. Mobile devices are their own little computers with their own file system, whereas web browsers are not. The differences can become quite significant. So there are two questions for a project like Appium that wants to use the WebDriver protocol to implement automation for mobile devices. The first is, what do we do with the commands that don't make sense on mobile, that are a part of the WebDriver spec? And the second question is, how do we implement support for commands that would be really useful for mobile automation, but aren't listed in the WebDriver protocol? The answer to the first question is pretty easy. If there's something that doesn't make sense for mobile, Appium could choose just to not implement it. And this is what Appium does. Although, in fact, Appium also provides support for mobile web browsers, so Appium ends up supporting the entire WebDriver protocol as it is anyway, at least for the web browser context. The answer to the second question about how to provide support for mobile-specific behaviors is a bit tougher. Ultimately, Appium wants to make sure that you have the automation capabilities you need, even if they go beyond the WebDriver protocol's boundaries. And the way we provide that support is by extending the WebDriver protocol. We add support for new commands, not by breaking the protocol, but merely by extending it. The protocol, as it stands for the web, is basically a big list of routes and rules about what sorts of parameters those routes expect and what sorts of responses they will generate. All Appium does is add a bunch more routes to that list. What this means is that if you want to know all the commands that Appium supports, you can't just go looking at the WebDriver protocol documentation. Because Appium has added a bunch of its own extensions, which would only be found in the Appium documentation, you need to go there in order to learn more about them. You can think of Appium's protocol as a superset of the WebDriver protocol. And this is in fact how the WebDriver protocol was designed and defined. The authors of the protocol knew that other projects might want to extend it with their own commands. So the protocol itself provides rules for how to do that in a way which is approved by the standard. And that's what the Appium team took advantage of. Let's briefly look at a few examples. These three examples represent the ability to lock a device's screen, unlock the screen, and check whether an app is installed on a device. None of these would make sense in the context of a web browser, so Appium added the commands as extensions to the protocol. Notice that for each of the routes, they all have a /Appium in the middle. This is to make sure that Appium's command extensions will never clash with official extensions to the protocol down the road. Otherwise, the Appium extensions work exactly the same way from a protocol perspective as their standard counterparts. They take the same types of parameters and respond with the same types of values or error messages. All this to say, it's good to be aware that Appium has extended the WebDriver protocol, in a standard compliant way to be sure, but it has extended it to provide additional features specifically for the purpose of automating mobile apps. Okay, at this point, we have covered the WebDriver architecture and protocol in depth, and also discussed how client libraries have been created to make it super easy for clients to address the Appium and Selenium servers. Now let's talk more about the server side, specifically for Selenium, and see how it works. First, let's recap what we mean by server. In our context, the server is the piece of the architecture which listens for automation commands, then actually implements those commands, and finally responds with the result of the command. It's the piece, in a word, that does all the heavy lifting. So we could say that the server has the responsibility of translating the WebDriver protocol into automation. To do that, it needs to be tightly integrated in some way with the platform that it's automating. If you want to automate the Chrome browser, then the server needs to be able to turn a request to click an element into the actual clicking behavior within Chrome. If you want to automate an iOS device, then the server would need to know how to do the same thing for iOS. In actual practice, there is no one server that can possibly know how to manage automation behaviors across all these different platforms. Even if we just consider web browsers, the major browsers all work so differently than one another under the hood that we really need a different way of translating WebDriver to browser automation for each of these. And this is exactly what we have. The typical language for this in the world of Selenium and Appium is that of the driver. The driver is a piece of software that can speak the WebDriver protocol on one end and translate it to automation for a particular platform on the other. In a way, it's just like browsers themselves. They're all independent implementations of the various web standards. And nowadays, each of the browser drivers is its own standalone piece of software, because WebDriver implementations are being produced by the makers of the browsers themselves, and not an independent party. So, for Chrome, we have something called Chrome Driver, which is released by Google. For Safari, we have a WebDriver automation server called Safari Driver, which is released by Apple. For Firefox, the equivalent is called Gecko Driver, which is maintained by Mozilla. And for Edge, it is rather predictably called Edge Driver, and it's developed by Microsoft. Each of these drivers are completely independent projects with no real shared code. And yet, they are all servers that implement the same WebDriver protocol. It's just that each of these drivers knows how to control their particular browser in response to WebDriver protocol commands. So, if all these drivers exist, what is Selenium exactly? Why do we need something else called Selenium if we can just automate all the browsers individually using these drivers, which act as standalone WebDriver protocol servers? Well, the simplest answer is that we don't need Selenium anymore. Selenium is the idea and the project that spawned all of these drivers. They used to be a part of Selenium itself, so that you had to run a Selenium server to access the capabilities of these drivers. But now that the browser vendors develop the drivers themselves, they have migrated out of Selenium and become their own projects. There are still a few reasons to work with Selenium in addition to working with these drivers directly. First, if you want to test more than one type of browser, you can connect each driver, each WebDriver implementation, to a Selenium server, so that you only have to have one running server to point your test automation scripts to, rather than requiring your scripts to know about all the different driver servers. Secondly, if you want to take advantage of a tool called Selenium Grid, which helps to manage a whole fleet of browsers for testing, then you'll need for your automation commands to hit a Selenium server rather than going directly to a driver server, because the browser drivers don't know or care anything about Selenium Grid. So that's basically the story for Selenium drivers. They're just servers that know how to automate particular browsers, and we can use any WebDriver client to connect to them. We can create sessions, find elements, and all the rest. Appium provides support for different platforms in much the same way that Selenium does, namely by the use of independent bits of software, each of which knows how to target one particular platform for automation. These bits are called drivers in the Appium world, just like they are in the Selenium world. Appium started out with one driver for iOS. Then Android support was added, bringing the driver count to 2. Eventually, many more drivers were created to target platforms beyond even mobile devices. Originally, just as with Selenium, all drivers lived inside the Appium codebase and were a part of the Appium software whenever you downloaded Appium. With Appium 2.0, the Appium project has adopted a model a little closer to the WebDriver ecosystem, where drivers are actually now independent from the main Appium server. There are still some differences between the two projects and how they organize drivers. Web browser drivers are maintained by the browser vendors, Microsoft, Google, Apple, Mozilla, and so on, whereas all the mobile drivers are still technically unofficial. From the perspective of Apple and Google, who develop iOS and Android, the Appium drivers for those platforms are just unofficial third-party projects. Another difference is that Selenium doesn't manage drivers for you on its own. Even if you want to use Selenium in front of your drivers, you need to figure out how to download and maintain the different versions of the drivers that you need. With Appium, however, you get a command line tool as part of the Appium software that lets you manage which drivers you have installed. On top of this, Appium actually has a bit more of a robust ecosystem for drivers. Appium itself provides tools for anyone in the world to write their own Appium driver to connect up automation for an existing or brand new software platform. And this makes sense. The goal of Selenium was to automate web browsers, and now each browser has its own driver maintained by the makers of the browser itself. But Appium's goal is a bit broader, namely bringing WebDriver-style automation to any and every platform. There's no way the Appium team can do that on our own. So instead, we provide tools that make it easy for any developer to create a new WebDriver implementation for a new platform. These new custom drivers can then easily be installed and shared with others using Appium's driver command line interface. So, what drivers currently exist for Appium? What are the so-called official drivers? Later on, we'll talk about ways to get a current list from the Appium software itself. But for now, we can say that there are basically 8 drivers that the Appium team officially recognizes. 2 for Android, 1 for iOS, and the rest for a variety of other platforms. And of course, as the driver ecosystem grows, this number will also increase. Let's talk about the iOS driver first. It's called the Appium XCUI test driver because it is based on the XCUI test automation technology from Apple. Next is the first of the 2 Android drivers. It's called the UI Automator 2 driver because it is built on top of Android's UI Automator 2 APIs. Third is a newer Android driver called the Espresso driver. Even though Espresso has an automation model quite different from UI Automator 2, which allows for gray box testing, the Appium team figured out a way to wrap it up in a WebDriver compatible interface. Fourth, we have the Appium Windows driver, which provides automation access to Windows desktop environments. The Windows driver is powered by a piece of technology produced by Microsoft called WinAppDriver, which is itself already a WebDriver compatible automation server. In this case, we do actually have something more similar to the situation with browsers, where the platform developer itself has put together a WebDriver compatible automation tool. Great job, Microsoft. Fifth, we have the Appium macOS driver, which is built on top of macOS's accessibility protocols for the purpose of automating macOS desktop apps. Unfortunately, it's not maintained by Apple itself, and it has a fairly limited feature set at the moment. The sixth, we have something called the Tizen driver. Tizen is a mobile operating system, competitive with Android and iOS, except it's produced by Samsung. It's used mostly in wearables and smart TVs. In this case, Samsung itself developed the Tizen driver, so it has great support for automating the Tizen platform. Next, we have the Flutter driver. Flutter is a native app development framework from Google, similar to Facebook's React Native framework. Flutter allows developers to write apps in the programming language Dart and have the framework, the Flutter framework, handle the conversion to native code for both iOS and Android. The Appium Flutter driver enables working with elements as defined in the Flutter layer, rather than only the ultimately produced native iOS and Android elements. Finally, as another example of a third-party driver, we have the UI TV driver, which makes automation easy for developers using the UI TV cross-platform TV app development framework. Now, in this course, we are obviously focusing on the use of Appium for testing mobile apps, which is far and away the most popular use case for Appium. By and large, what you learn here will also be relevant for other platform drivers too. But each driver has its own subset of the WebDriver protocol that it supports. And each driver might additionally support some features which are specific to that platform, or which only make sense on that platform. So it's always a good idea to familiarize yourself with the documentation for a particular driver when you begin to use it. In a perfect world, each Appium driver would implement the WebDriver protocol in exactly the same way across all platforms. But unfortunately, this is not always possible. The differences between the iOS and Android platforms, for example, are pretty vast compared to the differences between Safari and Chrome. Safari and Chrome both render web pages according to a certain standard, but there is no standard mobile app language or framework which iOS and Android both support. Because of this, the automation tools available for all the various Appium platforms differ in which features they provide, and in some cases, in how they implement the same features. Of course, the Appium team works as hard as we can to make sure that the same commands are available on both platforms, and to make sure that the same commands across both platforms ultimately result in the same behavior on the device. And sometimes I'll say this takes quite a lot of doing. But one consequence of the fact of these differences is that cross-platform test code is not always as easy to write as it is for the web. It's true that you might wind up in a situation where you need to write a bit of test code that does one thing on iOS and a different thing on Android. In those cases, there are often ways to structure your code to make it as clean as possible. We'll discuss those kinds of tricks later on. Currently, there's not more than one supported driver for a given platform, except in the case of Android. So for most platforms, the choice of which driver to use is easy. But what about Android? How do you know whether to use the Espresso driver or the UI Automator 2 driver? Unfortunately, this choice does matter a fair bit, since each driver works differently enough that you can't assume your tests will run without slight modification on both drivers. The way to pick a driver is to evaluate the underlying technologies used by the driver, as well as the feature set provided by the driver. Ultimately, you will want to stick with the driver for your test suite for quite some time, ideally the life of the test suite. In the case of Android, you could think about whether you need to automate apps apart from your own, for example. If so, you probably need to use the UI Automator 2 driver, because the Espresso driver doesn't support the multiple app use case. And indeed, in general, the UI Automator 2 driver supports more features, though the Espresso driver does come with a few features that the UI Automator 2 driver does not have, like the ability to target and execute code within your application directly. Anyway, before you start a new project, it's always a good idea to go through the available driver features and understand what the situation is, because you'll likely want to stick with your choice for some time. But what happens if you do find yourself in a position of having written a test suite using one Appium driver, and now you want to switch drivers for your platform to a newer one, or maybe one that's based on newer technology? This happened, for example, with iOS in quite a big way some years ago, when Apple deprecated their iOS UI automation JavaScript API and decided to support only XCUI test. All Appium users had to migrate their driver from the old iOS driver to the new XCUI test driver at that point. And I have to say that at the end of the day, this wasn't nearly as big of a headache as if these folks had written their tests using Apple's tools directly. With Appium, the API stayed stable. It stayed stable enough, anyway, that only a few small changes had to be made. And that is exactly the promise of Appium, that it provides a stable WebDriver-compatible API on top of a shifting set of underlying technologies. And of course, as far as possible, Appium drivers do try to implement the same set of WebDriver commands in the exact same way, so that migration and cross-platform scripting are a reality and not an impossibility. Let's start to think about how you would get a working Appium and Selenium installation set up on your local machine. The first thing we want to make sure is present is something called Java. Java is a programming language and a set of tools that are used by both Appium and Selenium. First of all, we can check to see if we already have Java on our machines. It often comes on computers by default nowadays, or you may have already installed it for another purpose, so it's a good idea to see if it's already there. To check if we have it installed, open up your terminal either on Mac OS or your command prompt on Windows, and run the echo command with the appropriate variable name after it. We'll talk more about environment variables in a little bit. So if we run this on Mac, we get output that looks something like this, /library/java/java virtual machines, and so on. Whereas for Windows, we get something that might look like C:\program files, \java, and so on. So that's nice, but if you didn't get anything printed out, what's going on there? And what are we actually doing with this command anyway? What is the point of all these commands? Well, on each platform, these commands are designed to print out the value of something called environment variable. So let's take a brief digression to understand environment variables, since they're important for getting Appium set up especially. Environment variables are just like variables in any programming language, like Python, like the variables we've been learning about there. They're little names, essentially, that can hold values, and they can change over time. Environment variables are designed to be variables that exist in the terminal or across your whole system. And environment variables are made available to any program that you run from the terminal session where the variable is defined. So any program you run from the command line can read any environment variables that are set in that particular terminal session. You probably already have lots of environment variables set by default, just without realizing it. For example, if you're on a Mac, open up a terminal and type echo and then the $ character and then the word home, all uppercase. You should get back something that looks like /users / well, in my case, jlips, but in your case, it would be your username. So this home character is an environment variable that defines the location of your user's home directory on the system. Or, if you're on Windows, open up a command prompt by going to the Windows button, typing CMD, and hitting Enter. And now we can type echo, and then the %, and then the word home path, all uppercase, and then a trailing %. You should get back something that looks like /users / and then your username, based on whatever your computer's username is. On either platform, what's going on is that the path to your home folder has been saved as an environment variable. Here are a couple more key points about environment variables. First, environment variables are only valid in the terminal session where they are defined. If you define an environment variable in one terminal window and then open up another one, the variable will not exist in the other one. There is a way to make variables persist across sessions, which we'll discuss momentarily. Second, to check the value of the environment variable, you can use the echo command, just like we did. When you echo out the value of a variable, on macOS, you put a $ in front of the variable name. And on Windows, you put % around the variable name, one on each end. Third, to set environment variables from the terminal, we can use the export command on Mac or the set command on Windows. For example, we can run export hello = world on macOS or set hello = world on Windows. In both cases, we don't use the $ or % when assigning values to the variables. Let's see this in action now. I'll run the export command first. Export hello = world. This defines the variable hello. And now I can try to echo it out by ensuring that I use the $ when I reference the variable for the purpose of echoing it. And sure enough, I get world printed out. But now let's try something else. I'll open up a new terminal window and run the same echo command. Echo $hello. What happens? I get nothing printed out, or more precisely, a blank line printed out, which means the variable is not defined. The hello variable is empty in this particular session. That's because my export command only set the variable in this other session. Variables don't span multiple sessions. But it's often really important to have environment variables set for one reason or another, and it's a pain to set them by hand every time you open a new terminal window. So let's talk about how to make it seem like we can persist these variables across sessions. On Mac, it looks like adding the export command that we just saw to something called a shell startup script. By the way, when I say the word shell, that's just another way of talking about the program we're using when we open up the terminal. This text-based command interface is called a shell. In fact, I can even echo out the shell environment variable, and it will tell me the program that I'm running as my shell. In my case, something called Z shell. For you, it might be bash or something else. So whenever you open up a shell in your new terminal window, the shell process tries to read certain files. These files are called startup scripts to see if you have put any commands in those files to be run automatically every time you open up a new session. And you can include environment variable exports in these shell startup scripts. The tricky part is figuring out which file you need to create or edit in order to have your shell read it on startup. On macOS, the file you can create or edit will depend on your operating system. If you have a version older than Catalina, the file will be called .bashrc, like this, .bashrc. That dot in front of it means that it's a hidden or invisible file. It won't show up in the Finder by default. And it needs to be located in your home directory. So to figure out if this file exists, we can run the following command. ls $home /.bashrc. What we're doing is running the ls command, which we'll talk about in a moment, and then constructing a path to send into it. This path starts off with $home, meaning we're actually using the value of the home environment variable. And then we're looking for a file called .bashrc within that home directory. A more concise way of doing this would be to type ls /.bashrc. On Mac and Linux, the tilde character is a shortcut to your home directory. So this command is basically asking the system to list the file called .bashrc in the home directory. Now, if you're on Catalina or higher, the default shell for macOS is something called ZSH or Z-shell, and its startup script file is .zshrc instead. So basically, look for a .bashrc or a .zshrc file as appropriate for your version of macOS. In all the instructions that follow throughout this course, I'll just mention the .bashrc file, so substitute the .zshrc file for your case as necessary. If you get a file name listed as the output of that ls command, great. Otherwise, if you get nothing or a message that the file doesn't exist, that's no problem. You'll just need to create one. So let's go ahead and open up a text editor, and we can either load or create that file. I'll get the open dialog up. Now, there's a problem here, however, which is that the dialog doesn't show hidden files by default. I'm in my home directory, but I don't see any hidden files. To get them to show up, I need to use a special Mac keyboard shortcut that works in any file dialog. I hit the keys Command, Shift, and period, the dot symbol all at once, and now I can see the hidden files. Again, that's Command, Shift, dot to show hidden files. Now I'll open up .bashrc. It might be empty or there might be other text in there for you. Either way, it's fine. If there is text in there, just ignore it. And we'll add something new at the very bottom of the file. So this would be the last line of the file, whether it's empty or whether there are other things in it. We'll run the same command we did on the command line earlier. Export hello equals world. Now we can save the file. And we'll go back to our terminal. And we'll close any open terminal windows. Now I'll open a new terminal window And I'll try the echo command again, echo hello. Now it should print out world, and it should do that in the future as well, anytime we open up a new terminal window. So that's how we set environment variables automatically for future terminal sessions on macOS. On Windows, it's a bit different, and it's best to use the system UI to make this change. First, I'll open up a command prompt and try to echo the variable we want to set to show that it's not yet set. So echo %hello %. Now this is strange. Instead of getting a value printed out, and instead of getting nothing printed out, we actually get the %hello % printed out. And this is just what Windows does when a variable is undefined. It just prints out the name of that variable again for some odd reason. Okay, now let's set up this custom environment variable. First, we want to open up the Start menu and start searching for environment variables. Now we can hit Enter, and it will open up a control panel item under System Properties and Advanced. Towards the bottom, we'll see a button that says Environment Variables. That's what we want, so we'll click that. In this window that pops up, we'll see two sections, one for user variables and one section for system variables. If you only care about setting these things up for your particular user, it's fine to do everything that we're talking about in the user variables section. Otherwise, put them in the system variables section. So now let's create a new user variable by clicking New in this section. This opens up a dialog where we can enter a variable name and a variable value. So we can enter hello as the name and world as the value, and then we can click OK. Now we can hit OK and OK out of all of these dialogues. And we want to close down our existing command prompt so that we can open up a new one and check that the environment variable is set. So I'll close that. And we can go back and type CMD in our Start menu to get a new terminal window. All right, now we can again type echo %hello %, and this time we get world printed back. So that's how we set environment variables persistently on Windows. Okay, back to making sure we have Java set up. Remember, the commands we ran to see if it was accessible via the right environment variable were echo Java_home on Mac or echo %Java_home % on Windows. If you got a value printed out there, examine it. Does the string JDK appear somewhere in it? And is the version number that follows 1.8 or higher? If so, you're in luck. It appears Java is already set up correctly. And what if you got something printed out, but it doesn't say JDK? Maybe it says JRE. Well, in that case, we'll need to download and install a new version of Java. And this is because Appium needs you to have something called the JDK, or Java Development Kit, because this version of Java has more tools bundled with it than the JRE, or the Java Runtime Engine does alone. Likewise, if you got nothing printed out at all, then it means your Java home variable is not yet set, and Java may not be installed and configured correctly. So let's talk about how to install it. The standard way to install Java is to head to java.com/download and follow the instructions for your platform. However, this takes you through a convoluted series of pages and clicks, so instead head directly to oracle.com/java/technologies/java se-downloads.html #java se-jdk, which is a long link but will save you some time in the long run. You will need to download and run an installer for the JDK from that page. Ensure it's the JDK and not the JRE. When you run the downloaded installer, make a note of where you install Java, because we're going to need that information later. So go ahead and pause this video and install Java now. Okay, now that you've installed Java, we need to set the special Java home environment variable. Let's do it on Windows first. Remember, when I say environment variable, I mean going through the steps appropriate for your system that we demonstrated earlier. So on Windows, we do this by opening up the environment variables area of the advanced system settings by typing in environment in our start menu, hitting enter, and clicking the environment variables button. Now we want to verify that a variable exists or create a new one called Java_home. And as the value, we set the path where you installed Java. In my case, I installed Java at c:/program/java/jdk 1.8.0_221. That's where Java was installed on my system, but you should use whichever path is correct for you. You might need to open up an Explorer window and figure out where it is. So that's how we set the Java home environment variable on Windows. Don't forget to close out your control panel settings. On macOS, it's a bit different. We know how to set environment variables in our bashrc file now, but how do we know where Java was installed so that we can set the Java home variable? To figure that out, it's easiest to use a little helper program that comes with Java. So we can open up a terminal, like I have here, and run the command /usr/libexec, libexec/Java_home. We'll hit enter and see what it prints out. For me, it's a path /library/java/java virtual machines/jdk 1.8.0 etc/contents/home. For you, it might look different. Regardless, this is the path you should use as the content of the Java home variable. Notice that here on macOS, it also looks a bit different than on Windows because it includes this contents/home directory. But anyway, I'll take this entire string, copy it, then I will open up my bashrc file that I was editing earlier, and I'll paste this whole thing in as the value of a Java home environment variable. So I set it using export, and then Java_home equals, and then I can paste in this value. Now, with any export command, there's something we need to be aware of. If there are any spaces in the value, we need to put that value in quotes. It's usually safe to always put things in quotes, so it's not a bad idea to just go ahead and do that now. And save the file. Great, now we have set Java home on macOS as well. Next, we're going to work with yet another environment variable. This one is called path. The purpose of the path environment variable is to define a list of directories. These directories are the ones your shell will look in when you want to execute a command. Why do we need to do this? Well, just because you have a program somewhere on your computer doesn't mean you can just type its name to run it from within a shell. You usually have to run it with the full path in front of it. Why would we want to run a program by its name rather than by a full path? Because some programs are so useful we end up using them in lots of places, and it would be tedious to have to type out the full path all the time. Now, the Java JDK comes with a lot of little programs, some of which Appium uses in order to do its work. It makes life easier to have all these little programs on your path. So the first step is figuring out where these little programs live. First, let's check out what's inside our Java directory by running a command that we saw earlier that allows us to list the contents of a directory. Again, on macOS, this is the ls command, which we can use in conjunction with our newly set environment variable, list Java_home. Nice, there's a listing of everything that's inside of our Java home directory. Or on Windows, we use the dir command, dir, to do the same thing. So let's try dir %java_home%. This is odd. It says the system cannot find the path specified, even though we had set the Java home environment variable. Let's try this. Let's put the variable reference inside some quotes. That worked that time. So what we've just learned is that when we actually want to refer to the value of an environment variable in conjunction with another command, we have to wrap the whole thing in quotes. But again, here is the contents of the Java home directory on Windows. In each case, what we'll get out is a directory listing. Notice a directory inside of our Java home folder called bin, B-I-N. Bin is short for binaries, and it's where all these little programs are. So what we want to do is make sure this bin directory is somehow a part of our path environment variable. To update the path variable on macOS, open up your bashrc file that you've been editing and check to see if any path variable is being exported in it. If so, you can just modify that line, or either way, and if not, you can create a new line at the bottom of the file that starts with export path equals $path. That's odd. The first thing we do is set path to itself. Why do we set path to itself? Well, path may have some values in it already set from some previous shell startup script that we can't see here. And we don't want to unintentionally clobber any information, overwrite any information, in other words, that might be contained in a pre-existing path variable. So what we want to do is first refer to the existing path variable and then add any new information to it. So let's change this line so that we write $path and then $Java home/bin. Okay, now we're using two environment variables to define path, any previous path value and our new Java home variable. Since we're using Java home, we need to write this path export line after we define Java home above. And all we're doing is telling the path that we want whatever is inside the bin directory inside Java home to be on the path. We can add as many directories as we want to the path by separating them with colons like we've done here. So each directory stands off against the others with colons. This is how we build up our list of directories in our path. Don't forget to save the file. On Windows, to update our path, we need to head to the environment variable editor as before. So environment, hit enter, and click the button. In either your user or system variables, you should see an existing variable called path. Click to edit it. The editor for the path variable is special. Instead of a single field for name and a single field for value, it shows you a list of paths. And you can add to this list by clicking New. So what we want to do is click New, and then add %java_home%\bin. And then we can save it to the list. Notice that again, we are using another environment variable, java_home, to help define the Java binary directory that we want to use in our path. This means that if we change the value of Java home down the line, say because we downloaded a new version of Java or something like that, we don't need also to update our path at that point. Some older versions of Windows have the path variable as one long string, not in this kind of nice interface, in which case you create the value just the same way that we do on macOS, by just putting a list of directories with a separator in between each one. In the case of Windows, however, the separator is not a colon, it would be a semicolon. But hopefully you get the nice interface that we have here. And don't forget to OK out of all of the control panel stuff. Okay, we have now set our Java home environment variable and our path variable in such a way that we should have access to the Java binary programs from our shell without needing to know where they are anymore. So we need to open up a new terminal or command prompt to read our new environment variables that we've set. And now let's try and run one of these little programs that is inside the bin directory inside Java Home. In this case, we'll try to run the Java command. If it works, you should get a bunch of help output from Java, like this. And note that whether you're on a Mac or on Windows, you can run the same Java command. If it doesn't work, if you didn't get output similar to this, then go back through these steps, or check the Java installation documentation or usage for your shell to make sure that you've set up your environment correctly. Remember, you can always echo environment variables to make sure they have the content you expect. For example, I can echo out Java_home, and I can echo out path as a way to verify that they are what I expect. And my path is very complicated. Yours might be less complicated. I've added a lot of things to it over the years. And on Windows, if you're doing this, obviously remember the %signs to get out the correct values. And there we go. Everything is good at this point if you've received the Java output above. So that's it for setting up Java and our Java environment, which will be very important down the line, especially for Appium. All right, let's talk about how to get Selenium set up. The first thing we need to do is make sure we have the browsers we want to test. In this course, I'm going to keep browser automation to 4 popular browsers: Firefox, Chrome, Safari, and Edge. You can download Firefox from Mozilla for any platform. Chrome likewise runs on any operating system. And technically, older versions of Safari do run on Windows in addition to macOS, but these older versions don't have the automation support that you would want. And finally, Edge runs on macOS as well as Windows, which is its native platform. And automation of Edge also works on macOS, so you can download Edge as well if you want to test it on your Mac computer. The next thing we need to do is get the drivers for each browser. These can be downloaded manually from each of the vendors' websites at the URLs shown on this slide. You don't need to worry about finding a driver for Safari, however, because Safari driver comes included with recent versions of macOS. When you go to download these, it's important to pay attention to the version of the browser that's supported by the driver that you're downloading. You always want to double check that you have a browser version which is compatible with the driver you're downloading. Sometimes there are incompatibilities which could lead to browsers and drivers not being able to talk to one another. For example, when developing this course, I had to actually download an older version of Edge driver, not the latest version of Edge driver, because the latest version of Edge for my operating system was not actually new enough to support the latest Edge driver. So feel free to pause the video right now and go and download each of these drivers that you want to try and run. Once the drivers are downloaded, we need to decompress them and decide where to put them. So for macOS, I have here the Gecko driver and Chrome driver archives that were downloaded to my desktop when I visited the links I shared in the slide. So I'll just double-click on each one to decompress it. When they're decompressed, you can see that what we have as a result is a single binary file for each of Chrome driver and the Firefox driver called Gecko driver. On Windows, these might be .exe files, of course, but either way, it is these binary programs that we care about themselves and not any directories they're currently in. You can put them anywhere on your system. I like to put it somewhere that I normally put these types of binary programs that I run from the command line. You can make yourself a new directory to hold this kind of stuff if you don't have one. Like I said, it doesn't really matter where you put it. For me, I'm going to open up a Finder window and navigate to a directory that I've created for this purpose called ~bin, so the bin directory inside my home directory. It's where I keep these kinds of things. And I'm going to copy Chrome driver and Gecko driver into this directory, making sure to replace any existing instances of them. Now, I said it doesn't matter where we put these, and that's correct. But what does matter is that we add the directory or directories containing our driver programs to our path environment variable. At some point, we need to do that. Now, if you don't remember what it looks like to set up the path environment variable, you can go back and watch the video on environment variable setup, where we talked about getting Java configured for our system. For now, I'm going to do this by opening up my .bashrc file again in an editor. So here it is, how we left it at the end of our Java setup. And I'm going to add my special bin directory to this path string using a colon, and then I'll enter the fully qualified path to my bin directory /users/jlibs/bin. Now, of course, if you do this on Windows, you'll need to go through the UI and use the appropriate type of path to add to your path string. Now, we should actually run these drivers that we downloaded to make sure they work. First, we'll stay on our Mac here and give this a try. So, let's get a fresh terminal. And now it should pick up our path changes. And let's just type Chrome driver to try and run the Chrome driver server, which we downloaded and put in our directory. This is not what we had hoped to see. Some kind of system alert that reads Chrome driver cannot be opened because the developer cannot be verified. This is unfortunately an error that we do need to expect, and it's due to macOS's security policies, which prevent programs from running if they've been downloaded through a browser, unless they've gone through an Apple notarization process. Now, Chrome driver hasn't gone through this process, but I'm fine running Chrome driver. I trust that I've downloaded it from a reputable site and everything. So now I'll show you how we can get around this error, because as you see, there's no way for me to actually allow this program to run using this message. So first thing we need to do is dismiss the dialog by clicking cancel. Then we head to the place on our file system where we've placed the Chrome driver file. For me, it's that directory /users/jlibs/bin, which I can get to by typing cd:/bin. So I've navigated here. If I want, I can list the contents of this directory, or I can try and list the Chrome driver file specifically to make sure that it's here, and indeed it is. Now that I know it's here, I can run a special command that alters some of the metadata for this Chrome driver executable file, so that macOS no longer knows that it was downloaded through a browser, and it will no longer complain when I try and run it. The command I need to run is called xattr, or xattr for extended attributes. And in this case, we're going to use the xattr command to remove a particular attribute from the Chrome driver file. In our case, it will be the aptly named com.apple.quarantine attribute. So we'll type xattr-r-d com.apple.quarantine, and then the name of the file that we want to remove this attribute from. In our case, Chrome driver. So we'll hit enter, run this command, and we've hopefully removed this quarantine attribute. So now we can try to run the Chrome driver server again. Excellent. This time we're greeted with a nice little welcome message that says starting Chrome driver at this particular version, running on port 9515, and so on. This tells us that the Chrome driver server is running, And we're now able to start connecting to it as a WebDriver client. Notice how, now that the server is running, we can't use the terminal anymore. I'm not able to type in commands and run them. That's because the server program here has taken over, and nothing else can run in the same terminal process until we either stop the server running or move its running to the background. So if you want to keep using this terminal, you can always open a new window and keep the server running in this one. For now, since we're not going to use the server, let's learn how to shut it down. To stop pretty much any program from continuing to run in the terminal, what we can do is press the following combination of keys, the Control key and the C key at the same time. Notice how we get this little caret symbol and the C printed out to show that we hit Control C and the server stopped. This is a pretty surefire way of killing something that's running. You'll end up using this key command many, many times over the course of your time with the shell, so it's a good idea to commit it to memory. Now, let's do the same thing with GeckoDriver. Try and run it. And unfortunately, the same security issue here prevents us from running it. So let's go through the same dance of removing the quarantine attribute, but this time with GeckoDriver. So xattr-r-d com.apple.quarantine, and this time GeckoDriver is the file that we want to modify. So I removed that quarantine attribute, and let's try and run the server. And now it's running. Great. GeckoDriver, like ChromeDriver, lets us know the host and port when it starts up. In our case for GeckoDriver, the default port is 4444, whereas ChromeDriver ran on port 9515. These ports don't really matter much, since if it comes down to it, we can always specify a specific port for either server. And we can stop GeckoDriver running the same way we did with ChromeDriver by hitting Control C. Finally, let's try running Safari Driver. Okay, we got some output, and as long as you get some kind of output, even if it's just this help output, you should be good to go. Oh, and one more thing for Safari Driver. By default, Safari doesn't allow itself to be automated by Safari Driver. We need to manually turn on that automation capability. You can do this through Safari's user interface, but the easiest way to accomplish the task is actually by running this new command in the terminal, Safari Driver --enable. It might be asking you for your password, in which case you can type it in. This turns on the developer feature within Safari that allows for remote automation. So now you should be good to go. On Windows, the process is very much the same. And in fact, it's easier since we don't have to deal with the security quarantine issue. So in my case, I'm going to open up an Explorer window and navigate to the directory where I've decided to put my 3 drivers. This directory is called bin inside of a code directory under my main user directory. And I put my 3 drivers here that I've downloaded for Windows, ChromeDriver, GeckoDriver, and MS Edge Driver. These were all the binaries that resulted from unzipping and decompressing the archives that I downloaded from the links that I shared earlier. Now, we need to make sure that this directory is in our path. So to do that, we start typing environment variable in the search box. Open up our environment variables, double-click our path, and make sure that the directory where these binaries are located is in the path. And I've already added it. You might need to add yours if you've created a new directory to host these files. And we can OK out of all of this. And now let's try to run some things by first opening up a command prompt. So open up a command prompt, and let's first try and run Edge Driver, because we are on Windows after all. So assuming that everything is on the path correctly, then we can just type ms edge driver And it should start up a server. Indeed, it says starting MS Edge driver at this version on port 9515. Seems a little bit similar to Chrome driver, now doesn't it? Very interesting. Okay, so the server started, and on Windows we can shut it down using the same key command as on Mac and Linux, Control-C. Now, let's do the same thing with Chrome driver. That works too. And finally, let's do the same thing with Gecko driver. Excellent. They all run just fine. So that's all we need to do to get the browser drivers installed and working successfully on both macOS and Windows. And one final note for the future while we're talking about system setup, especially on Windows. The first time you try and run tests using these servers, something called the Windows Defender Firewall might pop up and say that it blocked connections on localhost. That's because our WebDriver tests run as clients over a local network, and this can trigger the firewall to get a little concerned. It's really not an issue, but we don't want the firewall to block these connections because that prohibits all of the commands from going between client and server. So if you get this pop-up at some point, make sure you do allow communication on all the networks. The first time you do this, of course, your test might have already failed before you have a chance to allow the communication through, so you might need to run your test again. Just a note so that you're forewarned in case you see that down the line. What I showed you in this section was how to work with the browser drivers directly. This is a great way to work with them, but there are some easier methods for dealing with the drivers. These methods, while easier, do use some more advanced tools and knowledge, which is one reason I didn't think it was a good idea to introduce them here. On top of that, I wanted to emphasize that there's really no magic here at all. Just WebDriver servers, which have been produced by Apple, Google, Microsoft, and Mozilla, in which you can download and run like any other program. But one helpful alternative is a set of Docker images released by the Selenium community. If you're not familiar with Docker, it's a way of basically collecting groups of programs to run in a sort of sandbox. You can combine Docker images that contain browsers and drivers and orchestrate them all with something called Selenium Grid, also running in Docker. And this is definitely a setup to look at if you find yourself responsible for building out a browser testing lab. But with just getting a few drivers running on your local machine, we don't usually need to get to this kind of level of complexity, so there's no real need to think about Docker for now. But I just wanted to point out that if you do try and run a real production environment version of browser automation at some point, you'll want to look at a different solution like this. All right, let's talk about how to get Appium set up locally for both iOS and Android automation. Even if you ultimately choose to run your tests on an Appium cloud service, like HeadSpin, for example, I believe that it's important to be able to set up Appium locally. And you'll probably find it easier to follow along with the code examples by first developing them locally as well. So before we get started, let's have a look at the general requirements for each platform so you know what we're going to be installing and why. Now, for automation of both platforms, iOS and Android, and regardless of whether you're running macOS or Windows, the main dependency for the Appium server is a programming language runtime called Node.js. Node.js is basically like the Python command line tool that we've been using in this course. Node is a program that lets you execute other programs on your computer. Node.js is called Node.js because it is a platform for running JavaScript code in particular. If you're unfamiliar with JavaScript, JavaScript is a special programming language that was originally developed for running inside of a web browser. But it has proven to be a popular enough language that people wanted to run it on their servers as well, not just in the browser. Node.js is definitely the most popular way of running JavaScript code outside the browser. So why do we need Node.js in particular? Well, Appium is itself written to target the Node.js platform. So just like you need the Python programming language interpreter on your computer in order for you to run your Python test code, we also need Node.js on our computers in order to run Appium. Node.js and Python are similar in many ways, including the use of third-party packages or modules. When we're working with Python, we've been using a tool called pip, P-I-P, to install Python packages from the web and make them available in our environment. When we're working with Node.js, we use a tool called npm for the same purpose. All this to say, we will need Node.js and npm on our machine in order to download and run the Appium server. In addition to the Appium server, we'll need an Appium client of some kind. Since we're focusing on Python in this course, we'll need the Python interpreter, which we already have, thanks to our Python introduction earlier. We'll also need the Appium Python client, which we'll be able to download via pip. Now let's talk about what's required for Appium iOS automation. For iOS automation, we first of all need a Mac OS computer to connect to devices and host the Appium server. This means that, unfortunately, running iOS tests on Windows is not supported. Now, you can write and run test scripts themselves on Windows, as long as they connect to an Appium server over the network, which is running on a Mac. The main software requirement for iOS is the Xcode development environment. Xcode is a whole suite of development tools that Apple provides, mainly for the purpose of writing iOS, tvOS, and macOS apps. The way that Appium kicks off iOS tests relies on tools that come bundled with Xcode, so Xcode is a requirement. You don't actually need to use Xcode yourself as part of writing and running Appium tests. It just needs to be on your system and to have its additional command line tools downloaded and available for Appium to use. A second requirement is called Carthage. Carthage is a software package manager, much like pip or the node package manager we just talked about, npm. Carthage is specifically designed for Cocoa applications, which is to say applications developed for macOS, iOS, tvOS, etc. Appium uses Carthage as part of its XCUI test driver. This driver is written in part as a Cocoa app so that it can run on iOS. You don't need to think about or use Carthage directly. It just needs to be on your system so that the XCUI test driver can use it under the hood in order to build its own components the first time it runs. All right, so much for iOS. What about Android? What do we need to get that running? First of all, I want to point out that Android automation and setup can take place on macOS, Windows, or Linux, though I'm not going to go into detail about the Linux setup. Regardless of the platform you're running Appium on, the Android automation requirements are the same. The first requirement is the Java JDK, which we've already set up in a previous unit. The second requirement is something called Android Studio, which is sort of like Xcode, but is designed specifically for the purpose of developing Android applications. It's a whole development environment that lets you write and compile code in Java or another language used for Android development called Kotlin. It has a lot of special features that help with the visual design of Android apps, for example. Android Studio comes with a management system for versions of Android and for Android virtual devices, called the SDK Manager and the Virtual Device Manager. These are very important. Our third requirement is basically that we use this management system to actually install the tools and system images that go with particular versions of Android we want to automate. For example, if we want to run tests on Android 10, we'll need to make sure we have the Android 10 SDK, build tools, and virtual device system image. We'll look at how to get all of these shortly. Okay, let's do some practical steps to make sure our setup is going to work for iOS. The first step is to make sure you have Xcode. You might already have it if you've done certain kinds of software development on your Mac. You can check whether it's in your Applications folder or use the Spotlight searcher to search for it, just typing Xcode. If so, go ahead and launch it to make sure it works. If you don't have it yet, you can open up the App Store and search for Xcode in the App Store, and then make sure you install it by picking the correct application. Okay, so if you don't have it yet, go ahead and start installing it. Go ahead and start to do that now because it's huge, so it can take a significant amount of time to download. Feel free to pause the video and wait for that to continue. So now that you have Xcode, the next thing to do is open it up, as I've already done. When you launch it, the first time you run it, you'll be greeted with a dialog saying some additional components need to be downloaded. Go ahead and do this now. Otherwise, if you just get this Welcome to Xcode screen like I have, you should be set up with Xcode. But next, we need to double check that Xcode's command line tools have been installed correctly. To do this, we can open up a terminal and run a special command called xcode-select space and then a double dash install. So this runs a special Xcode program that will download additional command line tools that are required for Appium. You might get a pop-up or a message like I've just gotten here saying that they're already installed. And if so, great. Otherwise, click whatever buttons you need to click in order to allow the installation continue. Next, we want to open up Xcode and check what version of the iOS SDK it has come with. The iOS SDK, standing for Software Development Kit, is basically the set of libraries, software libraries, that are required to build iOS applications. To automate a particular version of iOS, say iOS 13, we need to have the iOS SDK for that version of iOS downloaded inside of Xcode. Each version of Xcode comes with the most recent version of the iOS SDK by default, so you may not need to download additional versions unless you want to test on something else. One way of checking which version of the SDK you have installed is to open up the Devices and Simulators window. We can do this by going up to the Window menu here, then opening Devices and Simulators. Click the Simulators tab, since we'll be working with simulators, and you should see a list of iOS simulators that have been installed. Click on any one of these, for example, iPhone 11, and in its details, you'll see which version of iOS it's designed to run on. In my case, iOS 13.6. Take a note of this version, because if it's different than the version I'm using in this course, down the line, you might need to update some code samples to run with your version instead, if it differs from 13.6. Okay, lastly for this Xcode setup, let's actually open up an iOS simulator to make sure it works. But first, what is an iOS simulator? A simulator is basically a virtual iOS device that runs on your macOS machine. It's not exactly the same as a real iOS device, and it doesn't have all the same low-level hardware stuff going on under the hood as a real device would. But it is a way to run and test apps that you're building without needing a physical iOS device. So it's quite useful. To open the simulator, we can go up to the Xcode menu, then to Open Developer Tool, then Simulator. One should start to launch immediately. It might be any kind of simulator. In my case, it's an iPhone 8. You can change the kind of simulator that's booted by going up to the File menu of the simulator app, then to Open Device, then to the iOS SDK version you want to open a simulator for, and then finally selecting the appropriate form factor. So I could choose to open up any of these instead of an iPhone 8 if I wanted. Okay, now we're ready for the last step of iOS setup, which is installing Carthage, the dependency manager that is used by Appium's XCUI test driver. The easiest way to install Carthage is to use, sadly, yet another package manager. Unfortunately, we have to use a lot of different technologies to get everything going here. This new package manager we're going to use is not for a programming language at all. It's actually for the macOS system itself. There are lots and lots of command line utilities out there that are convenient to use, and it's nice to have one consistent way of downloading and installing them on your machine. The way I like to do this is to use a tool called Homebrew. You can set up Homebrew by heading over to the website brew.sh and copying the installation command here under Install Homebrew. You can paste this into a terminal and run it, and Homebrew will be installed. So go ahead and do that now. Of course, I already have Homebrew installed. Once we have Homebrew installed, you can head to a terminal and run the Homebrew command that we use to install Carthage. It is brew install Carthage, like so. Go ahead and hit enter, and it will take a few minutes to download. Once it completes, you'll be good to go with all the iOS setup required for Appium. Okay, now let's move on to Android setup. First, you'll need to get Android Studio. To do this, you can go to developer.android.com/studio. Click the download link for your platform and run the installer as you normally would in order to install it as a new app. Once it's installed, go ahead and open it up. You'll be greeted with a splash screen that has a configure menu down at the bottom. When you open up this menu, notice that the top two options are called AVD Manager and SDK Manager. AVD stands for Android Virtual Device, and the AVD Manager is how we create and run Android virtual devices, otherwise known as emulators. Android emulators are very similar in concept to iOS simulators, though they differ in a lot of technical details. Android emulators actually implement an entire virtual device, down to the hardware. So even though they run on your computer as a virtual device, they're using all the same system code as would run on an actual physical device. We also have the SDK Manager here. SDK, again, stands for Software Development Kit, and it just means a collection of tools for building software. Let's first navigate into the SDK Manager. Opening up this menu item launches the preferences for Android Studio and takes you to the SDK Manager within them. The first thing to notice is the text field labeled Android SDK Location. The text in this box is a path to the location of the Android SDK on your disk. This is an important path for Appium because Appium works with the Android SDK, and so it needs to know where it is located on your system. Take a moment right now to write down or copy this path and paste it somewhere else because we'll need it in a moment. And don't be concerned if your path looks different from mine. It could be different depending on your system. Here in the SDK Manager, there are three main tabs: SDK Platforms, SDK Tools, and SDK Update Sites. let's first make sure we're on the SDK Platforms tab. This is a list of all the Android versions which you can download an SDK for. Basically, you need to download any of these versions that you want to run Appium tests on. For now, just make sure at least the latest stable version is installed. If there's no checkbox by it, make sure you check it. We'll eventually hit OK down here to install all the new software, but you can wait on that part for a moment. Now, let's go to SDK Tools. Here in this list of tools, there are 5 that you need to make sure are checked. First, the Android SDK Build Tools. Second, the Android Emulator. Third, the SDK Platform Tools. Fourth, the SDK Tools. And finally, the Intel x86 Emulator Accelerator. So make sure these are all checked and hit OK to go through the download process. At this point, you'll need to accept various license agreements and so on to download any new software. And as part of the install, if you're installing the Intel x86 Emulator Accelerator for the first time, it will open up its own installer. Please go through this installation process. You can keep all the default options that are recommended during install. Note that if you're on macOS, it's an expected outcome that the Intel x86 Emulator Accelerator install will fail the first time you run it, so don't be alarmed if that happens. But just a second, what is the Intel x86 Emulator Accelerator, otherwise known as HAXM? Well, HAXM is an extension for your computer that enables Android emulators to run much faster than they otherwise would, which is really important because they can be quite slow. One note for those of us that run macOS, at the end of installing HAXM, you might have gotten a message that a kernel extension was blocked from loading. This blocked from loading message looks something like this. And if this is an error that you got, then you need to open up your system preferences and head to the Security and Privacy preference pane, which looks like this. Here, you need to make sure you're on the General tab. Down at the bottom, you should see a message that says something like, software from developer Intel Corporation was blocked from loading. You can now click Allow to enable the extension. At this point, the extension may not be working correctly because it was blocked from installing. So you might need to actually run the installer again for it to complete installation successfully. And now, again, if you're on macOS, it's a good idea to open up a terminal to check if the HAXM extension is actually running. So let's open one up and run this command. KEXT stat, the pipe character, and then the words grep and Intel. You can hit enter. Now, what this command does is list out all the kernel extensions that are currently installed on the system. We do that using a special command called KEXT stat for kernel extension status. And then we filter that list for any lines that contain the string Intel, which you can see is highlighted here in the single line of output that I've received. Now, if you've never seen the pipe character in a command before, what it does is redirect the output of one command into the input of another command. So we're running this KEXT stat command and directing its output into another command, grep Intel. Now, grep is a command that allows filtering its input by some keyword that we care about, in this case, Intel, which is what filters the output of KEXT stat to only lines that contain the word Intel. Now, you don't really need to know about piping or grep for this course, but I mention it since it's always good to be learning a bit more about how to use the command line. Anyway, The moral of the story here is that if you see anything show up after running this command, it means the Intel kernel extension is loaded and functioning. If you don't see anything show up, it means that HeadSpin is not running. And if this is the case for you, you might want to try restarting your computer and or re-downloading, reinstalling HeadSpin, which you can also get directly from Intel's website, as sometimes messing with kernel extensions like we've done requires restarting the computer. All right, now that HeadSpin is set up, let's configure an Android virtual device, otherwise known as an emulator. To do that, we go back to Android Studio, click Configure, and then find the AVD Manager menu item. When the AVD Manager loads up, you probably won't have any AVDs listed here. Instead, you'll have a big button that says Create Virtual Device. If you have devices listed like I do, you can click the Create Virtual Device button down here. Now, what we can do is essentially walk through this wizard, which enables us to create a new virtual device based on any kind of hardware profile that we want. You can walk through this wizard with all of the default options, but make sure that for the system image, you choose the latest official release. At the time of creating this video, it is Android R, or API level 30. Now, if the official release isn't available for you, if there's a download link next to it, then you make sure to click the download link to download the system image so that you can create an emulator using that image. Then you hit next, and it's time to give the emulator a name. You can call it Appium, you can call it Test, call it anything that you want, as long as you can remember the name that you give it. Then you click Finish, and your virtual device will be created. In my case, I already have one. So once your virtual device is here in this list, to run it, you go over to the Actions column, and you can click the little green play button. So go ahead and do that now. It will take several minutes, but you should eventually see an Android virtual device go through a startup routine. Eventually, we can even play with it and notice how it behaves just like a real Android device in pretty much every way. Okay, there's one last thing we need to do to get our Android setup fully functional, and that is to set up the appropriate environment variables so that Appium knows where the Android SDK is installed. Do you remember that path that I asked you to save a bit earlier? Now's the time to use it. So if you lost track of it, you can always open up the SDK manager and look again at the path displayed near the top of that window. What we want to do now is set this path as the value of the Android home environment variable. So we'll head over to a terminal and get this going, but please refer back to the unit on environment variables when we installed Java if you want some help on making this happen. But basically, it looks like adding the export command to my shell startup script on Mac OS. So I'll do this now in my bashrc file, which is right here, and I can add the export command, export Android _home. So this is the name of the variable that we want to define. And we need to set it to the path that we found in the Android Studio SDK Manager. In my case, it's usr/local/adt/SDK, but yours might be different. Either way, you can save that. And of course, if we were on Windows, we would just do this by navigating through the control panel and adding the environment variable using the UI. Now, I have generally also found that it's useful to add several directories that are inside of Android Home to my path, so that I have access to Android-related commands from my terminal. Technically, this is optional, but I recommend you adjust your path in the way that I'm about to do here to include these directories as well. So first of all, because we want to reference the new Android home variable we created inside of our path variable, I first need to move it up a little bit so that it's above the path definition. Now we can start adding some directories inside of Android home to our path. We want things like Android home / platform tools. And as well, we want Android _home / emulator. And then a new path, Android home / tools. And then Android _home / tools / bin. So these are all the directories within the Android SDK that contain command line functions and tools we might want to use later. On Windows, the process is basically the same. Of course, you need to use the % signs, and you might want to add each path as a separate entry in the path list. Okay, that's it for Android. Now we are finally ready to install Appium itself. We're actually going to see how to install Appium in two separate ways. You can install Appium via the Node package manager, as we said before, but you can also download Appium as a graphical desktop app. I think it's important to know how to use Appium from the command line, so that's what we're going to do first. Now, the first thing we need to do is install Node.js and NPM. If you already have them, great. You can check whether they're already installed by running the commands node or npm in a terminal and seeing if they don't result in an error. If you run node, like I've done, it will take you into an interpreter session, so you can hit Control-C a few times to exit out of it. So make sure you have node and npm. If you just run npm, you'll get its help text if it's installed. If either of them aren't installed, the easiest way to install Node.js on a Mac machine is to run the command brew install node. Now, I'm not going to run it right now because I already have Node installed, but this is what you would do if you didn't. This uses the Homebrew System Package Manager to install Node and NPM, just like we did for Carthage. Now, for Windows, the easiest method is to head to the Node.js website download page at nodejs.org/en/download, and you'll get the appropriate installer for your system. Either way, make sure you run that installer and then open up a command prompt to run the node and npm commands that we did before. Again, that was just node, which brings up the interpreter, and npm, which should bring up the help text. If these things are the case, then node and npm have now been installed successfully. At this point, we can install Appium. Here we need to make a bit of a choice because the version of Appium that I am teaching in this course might or might not have been officially released by the time you're taking it. I want to teach you all Appium 2.0 or higher, which has a bit of a different way of managing drivers than the older Appium 1.x series. Appium 2.0 is currently still in beta at the time of developing this course, but it's ready for you to use to learn Appium. So let's run a little command to see what has been released on NPM at the present moment. npm info, then the name of the package we care about, which is Appium, and then a command about this package, dist-tags. This npm command will print out a little object that looks like JSON actually, that tells us which versions of Appium have been released to npm under different tags. So here, latest, beta, RC, and next are tags. What we're looking for is the name of the tag, which has a version of 2 point something after it. It might be latest by the time you're taking this course, in which case, great, let's use that one. Or it might be, as I've shown here, where the only tag that has a 2.0 or higher version next to it is called next. Whatever the tag is for you, remember the name of that tag. Now what we want to do is install that particular tag of Appium with this command, npm install -g Appium at, and now the name of the tag. So if 2.0 is on the latest tag, you can type latest. Otherwise, if it's like my screen here, we type next. Then we hit enter, and npm will go through the process of installing Appium. Now, the -g flag that we've used with the npm install command tells npm we want to make Appium available globally, so that wherever we are in our terminal, we'll be able to type Appium, and then we can run the server that way. Now, this command might take a while to run, but when it finishes, Appium should be installed. Note that if Appium was not able to be installed due to a permissions error, you might be tempted to retry the npm install command using the sudo privilege escalation tool. This is not a good idea, so if you're in this position, it's a better idea to change the ownership of your global node modules folder to make it possible to install node modules like Appium without using sudo. You can find guides online that will tell you how to find the location of this global node modules folder and how to update its ownership to your user using the chown command. Let's give Appium a whirl to make sure it was installed correctly. So we can just type Appium, and we should see some output that says Appium is listening. And moreover, that no drivers have been installed. So now that we have Appium itself, let's get the two drivers we care about. So I'm going to go ahead and hit Control-C to close out of the Appium server and clear my screen. Now, what happens if you typed Appium and instead of running the server, you got some error like the command could not be found? In that case, you'll need to do a little bit of research to figure out where npm has installed Appium on your system. And you need to make that directory available on your path. Hopefully you shouldn't have to do that, but if you do, then refer to the instructions for the particular way you installed npm so that you can figure out where it installs its packages and you can add that directory to your path. So, now to installing Appium drivers. The way we manage drivers using Appium is pretty easy. First of all, let's run Appium driver list. When we do that, we get a list of drivers and whether or not they are installed. We don't have any yet. None of them are installed. But we do see a list of drivers which we can install by name, including UI Automator 2 and XCUI test. So let's go ahead and install the XCUI test driver. Of course, we need to be on a Mac to be able to do this. Appium driver install, and then the name of the driver, XCUI test. Now, this command may have taken some time to complete, but when it does, run Appium driver list again to see that the driver is now registered successfully. So let's do the same thing with our Android driver and get it by typing Appium driver install, and then the name of the driver, UI Automator 2. Now we're pulling down the UI Automator 2 driver, which is the one we want. Okay. With these two drivers installed, that's it for Appium server setup. Now, let's talk about the other way of getting Appium, which is basically just downloading a UI version of it, called Appium Desktop. You can download Appium Desktop from its releases page at github.com/appium/appium-desktop/releases. So find the latest release and then download the installer or zip file for your platform from this list and start downloading it. It will take quite a while because it's a fairly large install. Now, I actually don't recommend using Appium Desktop for an Appium server, but it has some other tools that come with it that make it indispensable for writing your tests. What we're going to do in this course is to use the Appium Desktop Inspector tool, which we'll talk about later, in conjunction with our Appium server that's running on the command line. Anyway, once Appium Desktop is downloaded, go ahead and install it the way you would install any other app, and then open it up. Note that if you're on a recent version of macOS, you might get an error message about not being able to open the app due to it being from an unidentified developer. If you get this kind of message, then open up your system preferences, go to the security and privacy pane, and look for the ability to allow launching Appium Desktop. It's from that general pane in the system preferences, the way we did it for other software like Haxum. Likewise, if you're on Windows, keep in mind that the first time we actually use Appium Desktop, you might get some firewall warnings, which you'll need to use as an opportunity to give Appium Desktop permission to send and receive network data. All right, as long as Appium Desktop eventually launches like this, it's installed successfully, and that's all the setup that we're going to need to do that relates to Appium itself. At this point in the course, we have installed everything we need to run WebDriver scripts on browsers and mobile devices using Selenium and Appium. All that remains is to set up our local code environment so that we can begin to write test scripts. I'm going to slowly build out a project in subsequent courses along this theme, so you can start with me from scratch here. And don't worry, all the sample code that we type up will be available for download for you to look at, even if you're not following along in a hands-on way with me. Okay, the first thing we want to do is to create a directory somewhere on our system for our project to live. For me, I created a directory called ASF on my desktop, since this course was originally released as part of a larger course on Appium and Selenium called Appium and Selenium Foundations. It doesn't really matter where it is or what it's called, so you put yours wherever you want. I'm just going to open up a terminal now and navigate to it, so I am inside this directory from the command line. So I'll head to my desktop and then into the ASF directory that I had created there earlier. You can look inside this directory and see the subdirectory called Python, where we put all of our Python learning code earlier. And of course, if you're on Windows, the cd command will work, but you'll need to use a Windows style path like cd c:\users/your username/ wherever you have decided to put your directory. Okay, at this point, we need to get the Appium and Selenium client libraries installed so that we can use them to write Python test scripts. We're going to do this by using the pip command right here, pip, for downloading Python packages and making them available in our environment. If you're a Python developer and know about tools like virtual env or pyenv, that help keep Python projects in their own environments, feel free to create such an environment now. I'm going to do that myself since I use a tool called pyenv. If you want, I recommend looking up pyenv and learning how to use it yourself. Please feel free to do that. I'm not going to cover it in this course because it's not essential. You can certainly just install all your Python packages in your main default Python environment. But if you have pyenv up and running, you can run pyenv virtual env and then the name of a virtual env that you want to create, a virtual environment. I'm going to call mine ASF to make it the same as my code directory. So I can run this command and it will create an entire new Python environment with an area for me to install dependencies and keep them separate from the dependencies that are installed globally on my global Python install. Now, to get into the pyenv virtual environment, I say pyenv activate and then the name of the environment I want to activate, in this case, ASF. So now I am in my ASF environment and I'm ready to install some dependencies. So you can follow along with this now, whether you chose to follow along with pyenv or not. To install both the Appium and Selenium client libraries, we can run the command pip install Selenium, and then also Appium-Python-client with dashes in between, like so. These are just what the names of these client libraries happen to be on the Python package index. So if we run this command, it will install both the Selenium and the Appium client all in one go. So as we can see, it says that it successfully installed Appium Python client 1.0.2 and Selenium 3.141.0. But of course, your version numbers might differ if you've installed this at a different time than I have here. No matter what versions they are, it should be fine to use with this course. So now let's make sure that everything actually got installed correctly by starting up a Python interpreter, which we can do by just typing the word Python at the command line and then hitting enter. That will bring us into a Python interpreter where we can type out Python commands here and see what the result of those commands are in an interactive fashion. It's like a shell, but for just running Python commands. So the command I'm going to run is from Selenium import WebDriver, and I'll hit enter. If this line completes without any errors, without any exceptions being raised, and there's no output at all, then we know Selenium has been installed successfully because we were able to import the WebDriver module from the Selenium package. Okay, now we're going to do the same thing, but for Appium. From Appium, import WebDriver. So the only difference is that we're importing from the Appium package instead of the Selenium package. And again, if this is working, we'll see no output here. And at this point, we can exit the interactive environment using the exit command. This is just a Python function that we can call with no parameters. And now we've exited the interpreter. So at this stage, project setup is now complete and verified working.